In the vast expanse of space, beyond the twinkling stars and swirling galaxies we can see, lie some of the universe's greatest mysteries. These aren't just puzzles waiting to be solved. They're doorways to understanding the very nature of reality itself. Tonight, we're going to venture into the unknown, exploring questions that have left even the brightest minds in physics and astronomy searching for answers. Imagine a place where time itself breaks down, where light can never escape, and information seems to vanish forever yet somehow doesn't. These are black holes, and they're just the beginning of our journey. We'll explore regions of space so empty they shouldn't exist, forces so powerful they can alter the fabric of spacetime, and connections so strange they seem to frighten Einstein himself. What force is pulling thousands of galaxies, including our own, toward an unknown point in space? Why is the universe's expansion speeding up when gravity should be slowing it down? And what if empty space isn't really empty at all, but teeming with invisible energy we're only beginning to understand? These aren't just abstract questions. They're clues to the deeper nature of our universe, hints that our current understanding of physics might be just the surface of something far more profound. From mysterious signals that could be messages from other civilizations to massive bubbles of energy looming above and below our galaxy, we're about to explore phenomena that challenge everything we think we know about the cosmos. So lie back, look up at the stars, and prepare to question reality as you know it. Because in the next few hours, we're going to journey through some of the most extraordinary mysteries in the universe. Some might keep you awake pondering their implications, while others might just help you drift off to sleep, knowing that the cosmos is far stranger and more wonderful than we ever imagined. Our first stop? A place where the laws of physics themselves seem to defy explanation. The mysterious realm of black holes, where quantum mechanics and Einstein's relativity collide in a paradox that could revolutionize our understanding of the universe itself. The black hole information paradox stands as one of the most profound conflicts in modern physics, revealing a fundamental clash between two pillars of our understanding: quantum mechanics and general relativity. To understand this paradox, we need to explore what happens when something falls into a black hole and why two different branches of physics tell us completely different stories about its fate. According to quantum mechanics, information about a physical system can never truly be destroyed. If you burn a book, its information isn't gone. It's transformed into the precise arrangement of ash, smoke particles, and heat energy. In theory, if you could track every single particle and its state, you could reconstruct the original book. This principle is fundamental to quantum mechanics, and it has been verified countless times in laboratories worldwide. But black holes seem to break this rule entirely. When matter falls into a black hole, general relativity tells us it encounters the singularity, a point where space and time themselves break down. At the singularity, all properties of the infalling matter appear to be destroyed completely. According to Einstein's equations, only three properties of the black hole survive: its mass, its electric charge, and its angular momentum. Everything else about the infalling matter is erased. This creates our paradox. Quantum mechanics insists the information must survive, while general relativity says it must be destroyed. Both theories have been extensively tested and verified in their respective domains. Both cannot be correct when it comes to black holes. The plot thickens when we consider Stephen Hawking's groundbreaking discovery that black holes aren't entirely black. Through quantum effects near the event horizon, black holes slowly emit radiation and gradually lose mass. This process, known as Hawking radiation, eventually leads to the black hole's complete evaporation. But this makes our paradox even worse. If the black hole eventually disappears, what happens to all the information it contained? The radiation itself appears to be completely random, carrying no information about what fell into the black hole. This random thermal radiation can't preserve the quantum information of the original matter. It would be like having a library burned down and finding that the smoke contained only random patterns, with no way to determine what books were originally inside. Some physicists propose that perhaps the information remains locked inside a tiny remnant of the black hole that never completely evaporates. Others suggested that the information might be encoded in subtle correlations within the Hawking radiation, similar to how a hologram contains three-dimensional information in a two-dimensional surface. This latter idea led to one of the most revolutionary proposals in theoretical physics, the holographic principle. The holographic principle suggests that all the information about objects that fall into a black hole might be encoded on its event horizon, the boundary beyond which nothing can escape. This would mean the three-dimensional interior of a black hole is actually equivalent to a two-dimensional surface surrounding it. While this seems impossible, mathematics shows it could work, and the principle has become a cornerstone of modern theoretical physics. Another proposal suggests that the apparent destruction of information might be resolved through quantum entanglement across space and time. When matter falls into a black hole, it might become quantum entangled with its own Hawking radiation, preserving the information in a complex web of quantum correlations. This could explain how information escapes, but it creates new puzzles about the nature of space, time, and causality near black holes. The paradox becomes even more perplexing when we consider what happens at the event horizon from different perspectives. To an outside observer, infalling matter appears to slow down and never quite cross the horizon, while simultaneously being scrambled and encoded in the Hawking radiation. But to someone falling in with the matter, they pass through the horizon without noticing anything unusual before encountering the singularity. These two descriptions seem incompatible, leading to what's called the firewall paradox. Some physicists have proposed even more exotic solutions. Perhaps black holes connect to other universes through wormholes, and the information escapes there. Or maybe quantum effects prevent true event horizons from forming in the first place, replacing black holes with extremely dense fuzzballs of string theory states or other exotic objects that preserve information. The resolution to the black hole information paradox might require an even deeper revolution in physics. It suggests our understanding of space, time, and the nature of information itself might need radical revision. The paradox has led physicists to question basic assumptions about locality, the idea that objects can only influence their immediate surroundings, unitarity, the principle that quantum information is preserved, and even the nature of time itself. Recent theoretical work has suggested connections between the information paradox and quantum computation, proposing that black holes might be nature's most efficient computers, processing information at the maximum rate allowed by physical law. This connection hints at deep links between information theory, quantum mechanics, and gravity that we're only beginning to understand. The black hole information paradox remains unresolved, but its study has already revolutionized theoretical physics. It has led to profound insights about the nature of space, time, and information, suggesting they might be more fundamentally connected than we ever imagined. As we continue to probe this mystery, we might find that the true nature of reality is stranger and more beautiful than either quantum mechanics or general relativity suggest. On August 15, 1977, Ohio State University's Big Ear radio telescope captured 72 seconds of data that would become one of astronomy's most enduring mysteries. A powerful burst of radio waves, narrowly focused at a frequency that scientists had theorized might be used by alien civilizations, arrived from the direction of Sagittarius. The signal was so remarkable that astronomer Jerry Amon, reviewing the computer printout days later, circled the signal's intensity values and wrote "Wow" in the margin, giving the anomaly its now famous name. The signal arrived at 1.420 megahertz, remarkably close to a frequency that scientists had long speculated might be used for interstellar communication. This frequency is produced naturally by hydrogen, the most common element in the universe. Since any advanced civilization would likely understand the physics of hydrogen, this frequency range represented a logical channel for cosmic communication. What made the WOW signal truly extraordinary was its strength. Using the telescope's measuring system, where normal background noise registered as a blank space and increasing signal strengths were marked by numbers 1 through 9 followed by letters, this signal peaked at U, indicating it was 30 times stronger than the cosmic background. The signal's intensity rose and fell exactly as expected for a transmission coming from space, growing stronger and then weaker as Earth's rotation carried the telescope's beam across the sky. The characteristics of the transmission seem to rule out most natural explanations. Its bandwidth was less than 10 kilohertz wide, extremely narrow for a natural phenomenon. The signal appeared in only one of the telescope's twin feed horns and not in the other, suggesting a source that was fixed relative to the background stars, rather than something in Earth's atmosphere or a satellite in orbit. Despite the signal's strength, its precise origin remains uncertain. The design of the Big Ear telescope means the signal could have come from one of two different regions in Sagittarius, separated by a small distance in the sky. For decades, these regions appeared to contain no particularly remarkable stars. However, recent research has identified several sun-like stars within the signal's possible points of origin, including one star system about 1,800 light-years away. The most puzzling aspect of the WOW signal is that it has never been detected again, despite numerous attempts. In the months following the detection, Amon and his colleagues searched the same region of sky repeatedly. Other astronomers have conducted follow-up observations using more powerful instruments, including the Very Large Array in New Mexico and radio telescopes in Tasmania. All these searches have come up empty. This silence has led to various theories about the signal's origin. Some suggest it might have been a one-time burst from an unknown natural phenomenon. Others propose it could have been an intermittent transmission that we simply haven't caught again. Still, others wonder if it might have been a targeted message, broadcast once in our direction before moving on to other star systems. The possibility of the signal being human-made has been carefully considered and largely dismissed. The frequency band where the WOW signal appeared is protected by international agreement, reserved exclusively for astronomical research. While illegal transmissions do sometimes intrude into this band, none have ever matched the characteristics of the WOW signal. The idea that it might have been caused by a reflection off space debris has also been ruled out, as the required size and perfect positioning of such an object would be extremely improbable. More recent attempts to explain the signal have also fallen short. In 2017, a researcher suggested the signal might have come from hydrogen in the clouds surrounding two comets that were in the right region of sky. However, other astronomers quickly pointed out that the comets were not actually in the telescope's beam at the time of the detection, and that comets do not emit strongly enough at the observed frequency to explain the signal's strength. In 2022, the mystery drew renewed attention when researchers identified potentially sun-like stars in the signal's possible location. This discovery prompted the first coordinated observation of these stars using both the Green Bank telescope and the Allen telescope array. Despite being far more sensitive than the original Big Ear telescope, these modern instruments detected no sign of the mysterious transmission. The WOW signal stands as a reminder of how much we still have to learn about the universe. If it was a message from another civilization, it suggests that intelligent life exists, but might be trying to communicate in ways we haven't yet mastered. If it was a natural phenomenon, it points to physical processes we don't yet understand. Either way, it represents a genuine scientific mystery that continues to challenge our assumptions about what is possible. The signal has also influenced how we think about searching for extraterrestrial intelligence. Its brief appearance and subsequent silence highlight the challenge of detecting and confirming potential alien transmissions. Modern SETI projects now emphasize the need for continuous monitoring and rapid follow-up observations, lessons learned from our experience with this tantalizing but elusive signal. On the 35th anniversary of the detection, astronomers used the Arecibo radio telescope to send a reply toward the signal's origin point. The transmission included thousands of messages from Earth, though given the vast distances involved, any reply would take thousands of years to reach us. Like the original signal itself, this response represents humanity's enduring hope that we are not alone in the cosmos, and our desire to reach out across the stellar depths to whoever might be listening. Quantum entanglement might be the closest thing to magic that exists in our universe. Scientists have proven that two particles can instantaneously influence each other across any distance, an effect so bizarre that Einstein refused to believe it was possible. Yet numerous experiments have confirmed this phenomenon is real, leaving us to grapple with what it means for our understanding of reality. When two particles become entangled, they essentially become one system, no matter how far apart they are. Measure one particle, and you instantly know something about its partner, even if that partner is on the opposite side of the universe. This has been demonstrated repeatedly in laboratories using photons, electrons, and even small molecules. The phenomenon was first recognized in the 1930s when Einstein collaborated with Boris Podolsky and Nathan Rosen to publish a paper challenging quantum mechanics. They argued that quantum mechanics must be incomplete because it allowed for what Einstein called spooky action at a distance. According to their understanding of physics, nothing should be able to influence anything else faster than the speed of light. Yet, experiments have definitively proven Einstein wrong. In 1964, physicist John Stuart Bell devised a mathematical test to determine whether entangled particles were actually communicating instantaneously, or if they simply contained hidden instructions set at their creation. Decades of increasingly precise experiments have shown that the particles really do influence each other instantaneously, with no hidden variables involved. The most rigorous tests have been performed by groups around the world. In 2015, scientists conducted what they called a loophole-free test of quantum entanglement, closing all known potential explanations other than genuine quantum mechanical effects. They separated entangled particles by more than a kilometer and measured them so quickly that not even a signal traveling at the speed of light could have connected them. But what exactly happens during entanglement? When particles become entangled, their quantum states become correlated. For example, if two electrons are entangled in their spin states, measuring one electron to be spin up means its partner must be spin down. This correlation holds true no matter how far apart the particles are when measured. The strange part is that before measurement, according to quantum mechanics, neither particle has a definite spin state. They exist in a superposition of all possible states until observed. When we measure one particle, both particles instantaneously resolve into definite correlated states. This effect has been measured across distances of thousands of kilometers using satellites. Scientists regularly create entangled particles in laboratories using various methods. One common technique involves splitting a single photon into two lower energy photons, which emerge entangled. Another method uses atomic cascades where an atom emits two photons in quick succession. These techniques have become so reliable that researchers can now create millions of entangled particle pairs per second. The applications of quantum entanglement aren't just theoretical. Scientists are already using it to develop quantum computers, ultra-secure communication systems, and super-precise measurement devices. Quantum cryptography systems using entangled particles are already commercially available, offering theoretically unbreakable encryption. Yet profound mysteries remain. While we can prove entanglement exists and even use it practically, we still don't understand how it works. No one has explained the mechanism by which particles maintain their instantaneous connection across space. Some theoretical physicists suggest that our entire concept of space and distance might need revision. One interpretation proposes that entangled particles might be connected through higher dimensions, making their apparent separation in our three-dimensional space an illusion. Others suggest that at the quantum level, distance itself might not be fundamental. These ideas remain speculative, but they highlight how entanglement challenges our basic assumptions about reality. A particularly puzzling aspect of entanglement involves time. Quantum mechanics suggests that entanglement can work backwards in time as well as across space. Experiments have shown that particles can become entangled even if they never existed at the same time. This entanglement swapping has been demonstrated in laboratories, though its implications for causality and the nature of time remain hotly debated. The phenomenon also raises profound questions about the nature of information and reality itself. According to quantum mechanics, the information linking entangled particles travels instantaneously. Yet, we can never use this connection to send messages faster than light. This limitation, known as the no-signaling theorem, prevents violations of causality while still allowing the spooky action Einstein found so troubling. Current research continues to probe the boundaries of quantum entanglement. Scientists have successfully entangled ever larger objects, including thousands of atoms simultaneously. They've even proposed experiments to entangle living organisms, though such tests remain technically challenging. Each new experiment reveals more about how entanglement works, while deepening the mystery of why it exists. Perhaps most intriguingly, some physicists theorize that quantum entanglement might be fundamental to the structure of space itself. According to these theories, the entire universe might be held together by a vast network of quantum entanglement, creating what we experience as space and gravity. While this remains speculative, it suggests that Einstein's spooky action might be not just a curious phenomenon, but a cornerstone of reality itself. The significance of quantum entanglement received its ultimate scientific recognition in 2022 when physicists Alan Aspect, John F. Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics for their groundbreaking experiments. Their work spans decades, starting with Clauser in 1972, who was first to devise a practical test of quantum entanglement's strange properties. He measured the polarization of entangled photon pairs launched in opposite directions, providing the first experimental evidence that Einstein's hidden variables couldn't explain the results. Aspect then refined these experiments in the 1980s, developing methods to switch the directions of entangled photon pairs in billionths of a second after they had left their source but before reaching the detector. This ingenious approach closed a critical loophole in previous experiments, further confirming that quantum mechanics was telling us something profound about reality. Zeilinger later took this work even further, demonstrating in 1997 that quantum states could be teleported between particles, opening new frontiers in quantum communication and laying groundwork for technologies we're still developing today. These Nobel Prize-winning experiments didn't just validate quantum theory. They proved something remarkable about our universe: that Einstein, despite his legendary intuition, was wrong about quantum entanglement. The spooky action at a distance he refused to accept is fundamental to how our universe works, and we're only beginning to understand its full implications. In 1998, two teams of astronomers made a discovery that shook physics to its core. While studying distant supernovae to measure how the universe's expansion was slowing down due to gravity, they found something impossible. The expansion wasn't slowing at all. It was speeding up. This acceleration requires an enormous amount of energy pushing the universe apart, and we now know it makes up about 68% of everything in existence. We call it dark energy, and it remains one of the greatest mysteries in modern science. The discovery was so revolutionary that it earned the 2011 Nobel Prize in Physics. The teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, had used Type Ia supernovae as standard candles to measure cosmic distances. These particular supernovae always explode with the same intrinsic brightness, so by measuring how bright they appear from Earth, astronomers can calculate exactly how far away they are. What they found was that distant supernovae were dimmer than they should be, meaning they were farther away than expected. The only explanation was that the space between galaxies had expanded faster than predicted by normal gravity. This cosmic acceleration has been confirmed repeatedly through multiple independent methods, including studies of the cosmic microwave background radiation and the large-scale structure of galaxy clusters. The numbers are staggering. Every cubic centimeter of seemingly empty space contains a tiny amount of dark energy. While this energy is incredibly weak on human scales, it becomes overwhelming across cosmic distances. As the universe expands, it doesn't dilute like matter or radiation. Instead, the total amount of dark energy increases as space itself grows, creating a self-reinforcing cycle of faster and faster expansion. Current measurements indicate that dark energy's effects became dominant about 5 billion years ago. Before that, the gravitational pull of matter was strong enough to slow cosmic expansion. But as space expanded and matter spread out, dark energy's constant nature allowed it to eventually overcome gravity's weakening influence. If this continues, which observations suggest it will, the universe will expand forever at an ever-increasing rate. This creates a troubling future for our cosmos. Eventually, galaxies beyond our local group will recede faster than light, making them permanently unreachable and invisible to us. While this won't happen for many billions of years, it means there's a fundamental limit to how much of the universe we can ever observe or interact with. But what exactly is dark energy? Here, we must be clear about what we know versus what remains theoretical. The simplest explanation is that it's the energy of empty space itself, what physicists call vacuum energy, or the cosmological constant. Einstein actually included such a constant in his equations of general relativity, though he later called it his biggest blunder when he thought the universe was static. Quantum mechanics predicts that empty space should have energy from virtual particles popping in and out of existence. However, when physicists calculate how much vacuum energy there should be, they get a number that's wrong by 120 orders of magnitude. This has been called the worst theoretical prediction in the history of physics. The actual amount of dark energy we observe is tiny in comparison to these quantum calculations, and no one knows why. Alternative theories suggest dark energy might not be constant, but could change over time. These models, known as quintessence, propose a dynamic field that permeates space and varies in strength. While these theories remain speculative, they make predictions that astronomers are actively testing through observations of the early universe and the distribution of galaxies. Some scientists have proposed even more radical explanations. Perhaps our understanding of gravity needs modification at cosmic scales. Or maybe dark energy is leaking in from other dimensions predicted by string theory. While these ideas are mathematically intriguing, they remain highly speculative and lack observational evidence. What we can say with certainty is that dark energy exists. We've measured its effects through multiple independent methods, from supernovae to the cosmic microwave background to gravitational lensing. We know it makes up about 68% of the energy content of the universe. We know it causes cosmic acceleration and that this acceleration appears to be increasing. Everything beyond these established facts remains an active area of research. The implications of dark energy extend beyond cosmology. Its discovery suggests our most fundamental theories of physics are incomplete. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics governs the microscopic world of particles and forces. Dark energy seems to connect these realms in ways we don't understand, hinting at a deeper theory that might unite quantum mechanics and gravity. Major experiments and observatories are currently studying dark energy's properties. The Dark Energy Survey has mapped hundreds of millions of galaxies to track how cosmic structures evolved under its influence. The upcoming Euclid Space Telescope and the Vera C. Rubin Observatory will provide unprecedented data about dark energy's effects across cosmic history. Understanding dark energy may require a revolution in physics as profound as Einstein's theories of relativity. It challenges our basic concepts of space, time, and the nature of emptiness itself. The fact that most of the universe's energy exists in a form we barely comprehend reminds us how much we have yet to learn about the cosmos. Imagine dropping thousands of marbles onto a stretched rubber sheet and watching as they all slowly roll toward an enormous invisible weight hidden under the sheet's center. This is similar to what astronomers discovered in the 1980s when they realized that our galaxy, along with thousands of others, is being pulled toward a mysterious region of space with the mass of tens of thousands of galaxy clusters. This cosmic behemoth, which we now call the Great Attractor, lies approximately 220 million light-years from Earth on the border of the Norma and Triangulum Australe clusters. It's tugging on everything in our cosmic neighborhood with a gravitational force so powerful it overcomes the universe's expansion in our region of space. Our entire Milky Way galaxy, along with the local group and the Virgo supercluster, is moving toward it at over 1 million miles per hour. What makes this cosmic mystery particularly intriguing is that we can't directly see what's creating this enormous gravitational pull. The Great Attractor lies behind the center of our own galaxy, in what astronomers call the zone of avoidance. The region is obscured by the dense stars, gas, and dust of the Milky Way's central bulge, making traditional optical observations impossible. However, astronomers haven't been completely blind in their study of this phenomenon. By using observations in wavelengths that can penetrate the Milky Way's dust, including X-rays and infrared radiation, they've managed to peer into this hidden region. While these observations aren't perfectly clear, they've helped determine that the Great Attractor forms the central region of an even larger structure called the Laniakea supercluster, discovered in 2014. To understand the scale of these structures, consider that our Milky Way galaxy contains roughly 200 billion stars. The Laniakea supercluster, of which both we and the Great Attractor are part, contains about 100,000 large galaxies. The total mass concentrated in the Great Attractor region is equivalent to tens of thousands of Milky Way galaxies, creating an immense gravitational influence on our cosmic neighborhood. The movement of galaxies toward the Great Attractor follows a pattern astronomers call peculiar velocity. While the universe is expanding, causing most galaxies to move away from each other, some have additional motions caused by gravitational attraction. These peculiar velocities can reveal invisible mass concentrations, much like watching leaves blow in the wind can reveal air currents we can't see. When astronomers map these peculiar velocities, they find that galaxies are flowing along cosmic filaments, like rivers flowing toward a cosmic ocean. These filaments form part of the cosmic web, the largest known structure in the universe. The Great Attractor sits at a major intersection of these filaments, like a cosmic downtown where many highways converge. Recent studies using X-ray telescopes have revealed that the Great Attractor region contains several massive galaxy clusters undergoing collisions and mergers. These cosmic collisions heat gas to millions of degrees, causing it to emit X-rays that can penetrate the Milky Way's dust. This hot gas helps trace the distribution of dark matter, which makes up most of the Great Attractor's mass. The discovery of the Great Attractor led astronomers to identify even larger structures in the universe. Beyond the Great Attractor lies an even more massive concentration called the Shapley supercluster, which may be responsible for some of the gravitational effects we observe. These structures form part of a vast cosmic web of galaxy superclusters, connected by filaments and separated by enormous voids. Understanding the Great Attractor has practical implications for our measurements of the universe. To accurately measure cosmic expansion, astronomers must account for these local gravitational effects. The Great Attractor's pull creates deviations from the smooth expansion of space that must be carefully mapped and subtracted from observations. The existence of such massive structures also provides important clues about how the universe evolved. Computer simulations show that regions of slightly higher density in the early universe would naturally collapse into structures similar to what we observe. The Great Attractor and similar superclusters appear to have grown from these ancient density fluctuations through the action of gravity over billions of years. However, the Great Attractor's influence won't last forever. While its gravitational pull currently dominates our local cosmic neighborhood, the accelerating expansion of the universe driven by dark energy will eventually overcome this attraction. In the distant future, the Milky Way will begin moving away from the Great Attractor as dark energy's influence becomes dominant, fundamentally changing the dynamics of our cosmic neighborhood. Looking to the future, new telescopes and observing techniques promise to reveal more about this mysterious structure. Radio telescopes can peer through the Milky Way's dust, and gravitational wave detectors might eventually detect signals from massive objects in the Great Attractor region. Each new observation helps piece together the puzzle of this cosmic giant that's quietly pulling our galaxy through space. Picture our Milky Way galaxy not as it appears in photographs, but as it truly exists, surrounded by an enormous sphere of invisible matter that extends far beyond its visible edges. This is a dark matter halo, and every galaxy we've studied appears to have one. These mysterious structures make up about 27% of our universe, yet we can't see them, touch them, or directly detect them in any way. Our first hints of dark matter halos came from studying how galaxies rotate. In the 1970s, astronomers noticed something strange about spiral galaxies. Based on the visible matter we could see, stars at the outer edges should orbit much more slowly than those near the center, just as the outer planets in our solar system orbit more slowly than the inner ones. But that's not what they found. Instead, the outer stars maintained surprisingly high speeds, as if they were being held in place by some invisible mass. When astronomers calculated how much extra mass would be needed to explain these rotation curves, they discovered something astonishing. The visible portion of galaxies, all the stars, gas, and dust we can see, makes up only a tiny fraction of their total mass. The rest exists in these vast dark matter halos that envelope entire galaxies. In our own Milky Way, this invisible halo is staggering in scale. While the visible disk of our galaxy contains approximately 90 billion solar masses worth of material, the dark matter halo likely contains between 600 billion and 3 trillion solar masses. At our Sun's distance from the galactic center, measurements indicate there is about 0.0088 solar masses of dark matter in every cubic parsec of space. These halos aren't just static spheres. Computer simulations and observations suggest they have complex internal structures. The density of dark matter is highest near the galactic center and gradually decreases outward, following what scientists call an NFW profile, named after the astronomers Navarro, Frank, and White, who first described it. Unlike visible matter, which forms into the familiar spiral arms and disks we see in galaxies, dark matter remains distributed in this more spherical pattern. Dark matter halos played a crucial role in the formation of the galaxies we see today. In the early universe, ordinary matter was too hot and energetic to collapse into structures on its own. But dark matter, being immune to radiation pressure and other forces that affect normal matter, could begin clumping together under its own gravity. These initial dark matter clumps created gravitational wells that eventually attracted normal matter, allowing the first galaxies to form within these dark matter cradles. The process continues today. Dark matter halos grow through a process of hierarchical clustering, where smaller halos merge to form larger ones. When a small halo merges with a larger one, it can become a subhalo, orbiting within the larger structure. Our own Milky Way's dark matter halo likely contains thousands of these subhalos, some of which may host satellite galaxies, while others remain completely dark. The shape of dark matter halos tells us something about their nature. Unlike the perfectly spherical structures scientists first imagined, computer simulations suggest they're slightly flattened, more like ellipsoids. This shape comes from the way they formed, through the collapse of matter along cosmic filaments in the early universe. One of the most fascinating aspects of dark matter halos is their role in galaxy clusters. When clusters collide, astronomers can use gravitational lensing to map where the dark matter is located. The most famous example is the Bullet Cluster, where dark matter halos passed right through each other, while the visible matter interacted and slowed down, providing some of our strongest evidence that dark matter is real and behaves differently from normal matter. Despite their importance, we still don't know what dark matter halos are actually made of. Scientists have proposed various candidates, from exotic subatomic particles that rarely interact with normal matter to primordial black holes left over from the early universe. The leading theory suggests dark matter consists of what we call cold dark matter particles, massive particles that move relatively slowly and interact only through gravity. Alternative theories exist. Some scientists propose warm dark matter, which would behave slightly differently and might explain some observations that don't quite match the cold dark matter model. Others suggest modifications to our understanding of gravity itself might eliminate the need for dark matter entirely, though most evidence currently favors the dark matter explanation. What makes dark matter particularly puzzling is how it seems to break the rules we're familiar with. It doesn't emit light, absorb light, or interact with electromagnetic forces in any way we can detect. It appears to pass right through both itself and normal matter as if they weren't there. Yet, its gravitational effects are unmistakable, literally holding galaxies together and shaping the largest structures in our universe. Recent research continues to reveal new complexities in dark matter halos. They appear to rotate, though more slowly than the visible galaxies they contain. They're also dynamic structures, still growing and evolving as galaxies interact and merge. Understanding these halos better isn't just about solving a cosmic mystery. It's crucial to understanding how galaxies form and evolve, and ultimately to understanding our own place in the cosmos. In the 1930s, physicists Robert Oppenheimer and Hartland Snyder made a remarkable discovery while working with Einstein's equations of general relativity. Hidden within these mathematical formulas was something extraordinary: the theoretical possibility of white holes, cosmic objects that are the perfect opposite of black holes. While black holes are cosmic vacuum cleaners that only consume matter and energy, white holes would be cosmic fountains, forever expelling matter and energy while allowing nothing to enter. The mathematics tells us that white holes would share many properties with their dark counterparts. They would have mass, they could spin, and they could carry an electric charge. They would create powerful gravitational fields, bending space and time around them. But where nothing can escape a black hole's event horizon, nothing can enter a white hole's event horizon. It's as if the arrows of space and time themselves are reversed. This reversal creates fascinating theoretical predictions. While black holes form from collapsing matter, white holes would essentially run this process backward, expanding and ejecting material into space. Some physicists, including Stephen Hawking, have suggested that this property might connect white holes to one of the biggest mysteries in cosmology, the origin of our universe in the Big Bang. The idea stems from an important property of Einstein's equations. These equations are time-symmetric, meaning that for every solution describing a black hole consuming matter, there must be another solution describing a white hole expelling matter. This mathematical symmetry led to an intriguing possibility. Perhaps the Big Bang itself was a kind of enormous white hole, ejecting all the matter and energy that would become our universe. Recent theoretical work has expanded on this connection. Some scientists propose that when a black hole forms in one universe, it might create a white hole in another universe, with the two connected by a bridge through spacetime called an Einstein-Rosen bridge, or wormhole. While purely theoretical, this idea suggests that black holes might serve as cosmic engines, spawning new universes through white holes on their other side. However, there's a crucial catch. While white holes are mathematically possible according to Einstein's equations, they present serious problems when we consider how they might actually form. Unlike black holes, which we know can form when massive stars collapse, there's no known natural process that could create a white hole. If they exist, they would need to have been built into the very structure of the universe at its beginning. Even if white holes did somehow form, they would be incredibly unstable. Calculations show that even a single particle falling toward a white hole from the outside would cause fundamental problems with its structure. The white hole would either prevent the particle from ever reaching it by accelerating away faster than the speed of light, which is impossible, or it would be forced to violate the fundamental principle that nothing can enter its event horizon. The instability problem becomes even more severe when we consider that space isn't empty. The presence of any matter or radiation near a white hole would quickly destroy it. This means that even if white holes formed in the early universe, they would have disappeared long ago, leaving no traces for us to find today. Despite these challenges, white holes continue to intrigue physicists because they might help explain other cosmic mysteries. Some researchers have suggested that certain powerful gamma-ray bursts we observe might be the final moments of dying white holes. Others propose that white holes could explain some properties of quantum mechanics, particularly the phenomenon of quantum entanglement. A particularly fascinating development comes from loop quantum gravity, a theory attempting to reconcile quantum mechanics with general relativity. This theory suggests that when matter collapses into a black hole, instead of reaching an infinite density at its center, it might bounce back, transforming the black hole into a white hole. While still highly speculative, this idea offers a potential solution to the black hole information paradox. The concept of white holes also raises profound questions about the nature of time itself. If a white hole is truly the time reverse of a black hole, does this mean that regions of space could exist where time runs backward? While this seems to violate our basic understanding of cause and effect, quantum mechanics has shown us that the universe can be far stranger than our everyday experience suggests. Current observational evidence for white holes remains exactly zero. Despite decades of astronomical observations, we've never found anything that requires white holes to explain it. Every phenomenon once proposed as a potential white hole, from quasars to gamma-ray bursts, has been better explained by other astronomical objects and processes. Yet, the mathematics that predicts white holes remains solid, embedded in the same equations that successfully predicted gravitational waves, black holes, and the expansion of the universe. This creates an engaging puzzle for modern physics. Are white holes merely a mathematical curiosity, or do they represent something real about the structure of our universe that we haven't yet understood? Imagine taking a perfectly smooth sheet of ice and watching as it freezes. As it solidifies, tiny cracks form, creating lines of imperfection throughout the ice. Now imagine this happening to space itself in the earliest moments of our universe. These cosmic cracks are what physicists call cosmic strings, and if they exist, they would be among the most extraordinary objects in existence. First proposed by physicist Tom Kibble in the 1970s, cosmic strings would be incredibly thin, one-dimensional defects in the fabric of spacetime. While thinner than a proton, about 1/millionth of a billionth of a billionth of a meter across, their mass would be staggering. A single cosmic string, just 1 kilometer long, would contain more mass than Earth itself. These cosmic strings would have formed during the universe's earliest moments, just after the period of cosmic inflation, when the universe underwent its explosive initial expansion. As the universe cooled and underwent various phase transitions, similar to how water freezes into ice, the fabric of space itself could have developed these string-like defects. The way these strings affect space is fascinating. If you were to fly a spacecraft in a circle around a cosmic string, you'd discover something bizarre. The total angle around the string would be slightly less than 360 degrees. The string creates what physicists call an angular deficit, literally removing a tiny slice of space around itself. This distortion of space is so fundamental that even light passing by the string would be affected, potentially creating double images of distant galaxies. Despite their enormous mass, straight cosmic strings would exhibit a peculiar gravitational property. They wouldn't attract nearby matter in the usual way, unlike planets or black holes, which pull objects toward them. A straight cosmic string would have no gravitational pull on surrounding matter at all. The only gravitational effect would be on objects passing on opposite sides of the string, which would be deflected in different directions. However, cosmic strings wouldn't stay straight. Theory suggests they would move at incredible speeds, oscillating and creating a network of loops throughout the universe. When these strings intersect, they could form closed loops that break off from the main string. These loops would then oscillate under their own tension, gradually losing energy by emitting gravitational waves. For many years, astronomers thought cosmic strings might explain how galaxies first formed, with their immense gravity helping to clump matter together into the cosmic structures we see today. However, detailed observations of the cosmic microwave background, the oldest light in the universe, have shown that cosmic strings could have contributed no more than about 10% to the initial formation of galaxies. While we haven't directly detected cosmic strings yet, scientists have several ways they might find them. The violent oscillations of cosmic string loops should produce gravitational waves, ripples in space-time that we might detect with instruments like LIGO or the future space-based detector LISA. When cosmic strings intersect with each other, they could also create characteristic patterns in the cosmic microwave background radiation. There was excitement in 2003 when astronomers thought they might have found evidence of a cosmic string. They discovered what appeared to be two identical galaxies side by side, exactly what you'd expect if a cosmic string were creating a gravitational lensing effect. However, follow-up observations with the Hubble Space Telescope revealed they were actually just similar-looking but distinct galaxies. Another potential sign came from observations of a double quasar called Q0957 plus 561 AB. Scientists noticed that changes in brightness between the two images sometimes occurred simultaneously rather than with the expected time delay. Some researchers suggested this might be evidence of a cosmic string passing between Earth and the quasar, though this interpretation remains debated. The existence of cosmic strings would have profound implications for our understanding of the early universe. They would provide direct evidence of phase transitions that occurred when the universe was less than a second old, an era impossible to study directly with any other method. They might also help us understand the connection between quantum mechanics and gravity, as cosmic strings would be quantum mechanical objects large enough to have significant gravitational effects. Recent theoretical work has connected cosmic strings to string theory, the ambitious attempt to create a theory of everything. Some physicists suggest that what we call cosmic strings might actually be stretched out fundamental strings, the basic building blocks of matter in string theory that were dramatically expanded by the universe's growth. If true, finding cosmic strings could provide the first observational evidence for string theory. The hunt for cosmic strings continues with increasingly sophisticated tools. While their role in galaxy formation appears smaller than once thought, their detection would revolutionize our understanding of the early universe and potentially provide a window into physics at energy scales far beyond what we can achieve in any laboratory on Earth. In the constellation Bootes, 700 million light-years from Earth, lies one of the most mysterious structures ever discovered, an almost spherical region of nearly empty space called the Bootes Void, nicknamed the Great Nothing. This cosmic desert spans roughly 330 million light-years across and challenges our understanding of how the universe arranges its matter. The void's discovery in 1981 by astronomer Robert Kirshner and his team revealed something astonishing. In a volume of space where we should find around 2,000 galaxies, they counted only 60. The emptiness is so profound that if our Milky Way had been placed at the void's center, we wouldn't have known about other galaxies until the 1960s, because our most powerful telescopes wouldn't have been able to see any neighboring galaxies. The scale of this cosmic emptiness is difficult to comprehend. The void is so large that if you were traveling at the speed of light, it would take 330 million years to cross from one side to the other. To put this in perspective, when the first dinosaurs were appearing on Earth, light just starting its journey across the void would only now be reaching the other side. What makes the Bootes Void particularly puzzling is its structure. The few galaxies it does contain aren't scattered randomly throughout the void. Instead, they form a peculiar tube-like arrangement through its center. This unusual distribution suggests that the void might have formed through the merger of smaller voids, similar to how soap bubbles combine to create larger ones. The existence of such an enormous empty region presents a challenge to our models of how the universe evolved. According to our current understanding, matter should be distributed somewhat evenly throughout space, with natural variations creating clusters and voids. But the Bootes Void is far emptier than our models would predict. Scientists now believe these supervoids form through a process called baryon acoustic oscillations, pressure waves that moved through the early universe like sound waves through air. These waves could have pushed matter into certain regions, leaving other areas relatively empty. Over billions of years, gravity would have enhanced these differences, making the empty regions emptier and the dense regions denser. The void doesn't violate our fundamental theories of cosmology. In fact, it fits within the lambda CDM model, our current best explanation for how the universe evolves. But its extreme size and emptiness push these theories to their limits, forcing scientists to refine their understanding of how cosmic structures form and evolve. The Hercules supercluster forms part of the void's nearest edge, creating a stark contrast between the densely packed galaxies of the supercluster and the emptiness beyond. This boundary helps astronomers study how galaxies behave at the edges of such cosmic deserts and how matter flows around these enormous empty regions. Recent studies suggest that the Bootes void isn't unique. Astronomers have discovered other supervoids throughout the observable universe, though none quite as dramatic or well-studied. These voids appear to be part of a vast cosmic web, where galaxies cluster along filaments, leaving enormous bubbles of nearly empty space between them. Understanding these voids has become crucial to our comprehension of dark energy, the mysterious force causing the universe's expansion to accelerate. Voids like Bootes might help explain how dark energy works, as these regions show us how space behaves when it's almost completely empty of normal matter. The void also serves as a laboratory for testing theories about galaxy formation. The few galaxies within it appear to have evolved in isolation, largely untouched by the gravitational influences and collisions that shape most galaxies. This makes them valuable specimens for understanding how galaxies develop without external interference. Despite its emptiness, the Bootes void continues to fill our understanding of the cosmos. Its existence raises fundamental questions about the universe's earliest moments and the forces that shape the cosmic landscape we see today. As our telescopes and detection methods improve, this great cosmic desert may hold more clues to the universe's deepest mysteries. Try to picture a star so powerful that it could erase your credit cards from a distance of 192,000 miles, halfway to the moon. A cosmic object with a magnetic field so intense it could tear apart your body at the atomic level from 1,000 kilometers away. This is a magnetar, one of the most extreme objects ever discovered in our universe. Born from the death of massive stars, magnetars are a rare type of neutron star, the collapsed core left behind after a supernova explosion. While all neutron stars are incredibly dense, with just a spoonful weighing as much as 100 million tons, magnetars take things to another level entirely. Their magnetic fields are 1 trillion times stronger than Earth's, making them the most magnetically powerful objects known in the entire cosmos. To understand just how extraordinary these objects are, consider this. The strongest magnetic field ever created by humans is barely 1 million Tesla. A magnetar's magnetic field reaches 10 billion Tesla. At this strength, atoms themselves become warped, stretched into long, thin cylinders. A hydrogen atom near a magnetar becomes 200 times narrower than normal. The very vacuum of space becomes twisted, with light itself bending and splitting in ways we see nowhere else in nature. But what makes these cosmic monsters truly mysterious is their origin. Only about 1 in 10 supernovae creates a magnetar instead of a normal neutron star. Scientists believe the key lies in the star's final moments. As the massive star collapses, something extraordinary happens. The combination of rapid spinning, intense heat, and complex fluid movements creates a dynamo effect, similar to how Earth generates its own magnetic field, but cranked up to unimaginable levels. The first hint of these bizarre objects came on March 5, 1979, when an explosion of gamma rays hit several spacecraft around the solar system. The burst was so powerful, it sent radiation detectors off the scale, registering over 200,000 counts per second when normal readings were just 100. What made this event even more remarkable was that its source lay in the Large Magellanic Cloud, 163,000 light-years away. We now know of just 24 confirmed magnetars in our galaxy, though scientists estimate there could be as many as 30 million inactive ones lurking in the Milky Way. Their active lives are incredibly short by cosmic standards, lasting only about 10,000 years before their magnetic fields decay and they fade into silence. But during their brief lives, magnetars put on spectacular shows. Their powerful magnetic fields cause frequent starquakes on their surface, massive disturbances that release enormous bursts of energy. The most powerful recorded burst came from a magnetar called SGR 1806-20 in 2004. Located 50,000 light-years away on the far side of our galaxy, it released more energy in 1/10 of a second than our Sun emits in 100,000 years. These bursts create another puzzling phenomenon. Some magnetars occasionally emit fast radio bursts, incredibly bright flashes of radio waves that last just milliseconds. For years, the origin of these mysterious signals baffled astronomers. But in 2020, scientists finally caught a magnetar in the act, watching as it produced exactly the kind of radio burst they had been studying. Perhaps most intriguing is what magnetars tell us about the extremes of physics. Their surface gravity is so intense that the tallest possible mountain on a magnetar would be barely a centimeter high. Their magnetic fields are strong enough to affect the behavior of subatomic particles in ways we can only theorize about. Some scientists even suggest that magnetars might help explain some of the brightest supernovae ever observed, their powerful magnetic fields providing extra energy to make these explosions even more spectacular. Even more mysteriously, we have discovered magnetars orbiting dangerously close to supermassive black holes, like the one named PSR J1745-2900 near the center of our galaxy. How these incredibly magnetic objects interact with the extreme gravitational fields of black holes is still poorly understood. The existence of magnetars forces us to confront the limits of our understanding of physics. In their incredible magnetic fields, quantum mechanics and gravity interact in ways we cannot yet fully explain. They represent a cosmic laboratory for testing our most fundamental theories about how the universe works, all wrapped up in an object barely 20 kilometers across. Yet for all their power, magnetars remain elusive. We can only study them from a safe distance, as their magnetic fields would be instantly lethal to any spacecraft that ventured too close. They remind us that even after centuries of astronomical discoveries, the universe still holds mysteries that challenge our understanding of the fundamental forces that shape our cosmos. Close your eyes and picture looking out at the oldest light in the universe, a cosmic photograph taken just 380,000 years after the Big Bang. everything appears exactly as our theories predict. A nearly uniform glow with tiny ripples of temperature variations, except for one spot. There, in the constellation Eridanus, lies something that shouldn't exist, an enormous region of inexplicable cold that has left scientists puzzled for decades. This is the cold spot, a vast cosmic anomaly that spans an area of sky roughly 5 degrees across, large enough to fit 10 full moons side by side. While this might not sound impressive at the distances we're talking about, this translates to a structure billions of light years across. But what makes the cold spot truly remarkable isn't its size, it's its temperature. This region is 70 millionths of a degree Kelvin colder than its surroundings, with some areas plunging to 140 millionths of a degree below the average. In the carefully balanced early universe, such a dramatic temperature swing should be virtually impossible. When scientists first discovered the cold spot using the Wilkinson microwave anisotropy probe in 2003, many assumed it was an error in their measurements. But in 2013, the Planck satellite confirmed its existence. The cold spot was real, and its very presence challenged our understanding of how the universe formed. The mystery deepened when astronomers realized just how unlikely this cosmic anomaly is. According to our best models of the early universe, the chance of finding such a large cold region through random quantum fluctuations is less than 2%. This might not sound too extreme until you consider that these models have successfully predicted virtually everything else we observe in the cosmic microwave background with incredible precision. Several competing theories have emerged to explain this cosmic mystery. Perhaps the most mundane, though still extraordinary, is the supervoid hypothesis. According to this idea, we are looking through an enormous empty region of space, a billion light-years across and virtually devoid of galaxies. This cosmic desert, sitting between us and the ancient light of the cosmic microwave background, could create the illusion of a cold spot through a process called the integrated Sachs-Wolf effect. But even this explanation poses problems. If the cold spot is indeed caused by a supervoid, it would be one of the largest structures ever discovered in the universe, nearly 1,000 times larger than typical cosmic voids. The void would need to stretch across 1 billion light-years and be located between 6 and 10 billion light-years from Earth. Some scientists argue that such an enormous empty region is even more improbable than the cold spot itself. This has led to more exotic explanations. Some cosmologists suggest we might be seeing the aftermath of a cosmic collision, an ancient impact between our universe and another universe during the earliest moments of creation. Like ripples in a cosmic pond, this collision would have left a permanent mark in the fabric of space-time, visible today as an unusually cold region in the cosmic microwave background. This interpretation ties into string theory and the concept of the multiverse, the idea that our universe might be just one of many, existing like bubbles in an infinite cosmic foam. If true, the cold spot might be more than just an anomaly. It could be the first empirical evidence of another universe beyond our own, a window into the larger multiverse that has until now existed only in theoretical physics. The theory makes a bold prediction. If the cold spot truly represents a collision with another universe, there should be a similar anomaly on the opposite side of the sky. Some researchers claim to have found evidence of such a northern cold spot, though the data remains controversial. The search continues, as confirming such a counterpart would dramatically strengthen the multiverse interpretation. Yet another possibility suggests the cold spot might be evidence of a cosmic texture, a kind of defect in the fabric of space-time left over from the universe's earliest moments. These textures would be like cosmic knots formed during phase transitions in the first fraction of a second after the Big Bang, when the universe cooled and fundamental forces separated from one another. The debate over the cold spot's origin remains unresolved. In 2021, the Dark Energy Survey provided new evidence supporting the supervoid explanation, but questions still remain. The cold spot appears to be too cold to be explained by a void alone, suggesting that even if the supervoid exists, it might not be the complete story. What makes the cold spot particularly fascinating is how it challenges our assumptions about cosmic uniformity. The standard model of cosmology assumes that the universe should look roughly the same in all directions on large scales. The cold spot, along with other large-scale structures, suggests the cosmos might be more lumpy and irregular than our theories predict. As our instruments improve and our surveys of the sky become more detailed, the cold spot remains a reminder that the universe still holds profound mysteries. Whether it represents a supervoid of unimaginable scale, evidence of a cosmic collision with another universe, or something else entirely, it stands as a humbling testament to how much we have yet to learn about the cosmos. In the vast expanse of space, nothing outshines the raw power of a gamma-ray burst. These cosmic explosions stand as the most energetic events in the universe since the Big Bang itself, unleashing in mere seconds more energy than our Sun will produce over its entire 10-billion-year lifetime. They arrive without warning, blazing across billions of light years to tell tales of stellar death and cosmic catastrophe. Scientists first discovered these mysterious flashes in the 1960s, when American military satellites designed to monitor nuclear tests began detecting powerful bursts of gamma radiation coming from deep space. For decades, their true nature remained one of astronomy's greatest mysteries. These bursts appeared to come from all directions, yet their incredible brightness suggested they must be relatively nearby. It wasn't until the 1990s that we finally understood these events originated in the farthest reaches of the cosmos. Today, we know gamma-ray bursts come in two distinct varieties. Short bursts, lasting less than 2 seconds, arise from the violent collision of two neutron stars spiraling together in a deadly cosmic dance. As these incredibly dense stellar remnants merge, they create a black hole while spraying out jets of energy and heavy elements into space. This cosmic forge creates gold, platinum, and other precious metals, flinging them across the galaxy. Long bursts, lasting anywhere from several seconds to several minutes, tell an equally dramatic story. They mark the death of massive stars far larger than our Sun, in an event even more powerful than a typical supernova. When these giants exhaust their nuclear fuel, their cores collapse into black holes, while their outer layers are blown into space. For reasons still not fully understood, this process sometimes creates tightly focused jets of energy that drill through the dying star at nearly the speed of light. The raw power of these events defies comprehension. A typical gamma-ray burst focusing its energy toward Earth from even billions of light-years away can briefly outshine everything else in the visible universe combined. The most powerful burst ever detected, GRB 080319b, was so bright that it could have been seen with the naked eye from Earth despite occurring 7.5 billion light-years away. Yet their extreme brightness is only part of what makes gamma-ray bursts so remarkable. They also serve as nature's most powerful laboratories, creating conditions we could never hope to replicate on Earth. In the jets of a gamma-ray burst, matter is accelerated to 99.999% of the speed of light. The magnetic fields generated can be 1,000,000 billion times stronger than Earth's. The temperatures reached are tens of millions of times hotter than the center of the Sun. These conditions are so extreme that they push the boundaries of known physics. Scientists studying gamma-ray bursts have observed phenomena that challenge our understanding of how matter and energy behave, including particles that appear to move faster than light due to complex relativistic effects. The bursts also provide natural experiments for testing theories about quantum gravity and the structure of space-time itself. Despite decades of study, many mysteries about gamma-ray bursts remain unsolved. We still don't fully understand the mechanism that creates their incredibly focused jets of energy. Some bursts show puzzling patterns of brightening and dimming that don't match our models. Others appear to last much longer than they should, suggesting there might be additional types we don't yet understand. Perhaps most intriguingly, gamma-ray bursts might play a role in the cosmic story of life itself. A burst occurring too close to Earth could be catastrophic, with some scientists suggesting that past mass extinctions might be linked to nearby bursts. The intense radiation could destroy the ozone layer, exposing life on Earth to deadly ultraviolet radiation from the Sun. Some researchers even propose that gamma-ray bursts might help explain why we appear to be alone in our cosmic neighborhood, as these events could sterilize large swaths of galaxies. The future of gamma-ray burst research looks bright, with new telescopes and observatories joining the hunt. Modern satellites can detect about 1 burst per day, though we believe this represents only a small fraction of the true number occurring in the visible universe. Most bursts are never detected because their jets of energy are pointed away from Earth. Each new discovery brings fresh surprises. In 2020, astronomers found evidence linking some gamma-ray bursts to magnetars, incredibly magnetic neutron stars that might power these cosmic explosions in ways we're only beginning to understand. In 2022, observations revealed the brightest burst ever detected, GRB 221009A, providing an unprecedented opportunity to study these events in detail. As our instruments improve and our understanding deepens, gamma-ray bursts continue to illuminate the extreme physics that shapes our universe. They serve as cosmic lighthouses, allowing us to probe the very earliest epochs of cosmic history and study how the first stars and galaxies formed. In their afterglows, we can study the composition of the intergalactic medium and witness the forging of the heaviest elements in the universe. These cosmic beacons remind us that the universe is far more dynamic and violent than it appears to our eyes. In their brilliance and mystery, gamma-ray bursts stand as testament to how much we have yet to learn about the most powerful forces shaping our cosmos. Deep in the cosmic web that forms the large-scale structure of our universe lies a mystery that challenges our understanding of physics itself. Quasars, ancient and impossibly bright beacons powered by supermassive black holes, are organizing themselves in ways that should not be possible. Across distances of billions of light years, far too vast for any known force to act, these cosmic powerhouses are rotating in eerily similar directions. This peculiar alignment was discovered when astronomers at the European Southern Observatory used the Very Large Telescope to study 93 distant quasars. These objects existed when the universe was just 1/3 its current age, appearing as brilliant points of light powered by supermassive black holes actively devouring surrounding matter. Each quasar outshines its entire host galaxy, making them visible across the cosmos. The discovery came in layers, each more perplexing than the last. First, scientists noticed that some quasars' rotation axes pointed in the same direction, despite being separated by unfathomable distances. This alone was strange enough to warrant further investigation, but when researchers looked deeper, they found something even more remarkable. These aligned quasars weren't oriented randomly in space. Instead, their rotation axes aligned with the vast cosmic filaments and structures in which they resided. To understand the significance of this discovery, we need to appreciate the scale involved. The cosmic web, made up of galaxy filaments and clusters separated by enormous voids, represents the largest known structure in the universe. These filaments stretch for billions of light years, forming a vast network that defines the large-scale architecture of space. Finding quasars aligned along these structures suggests a level of organization that our current models of physics struggle to explain. The chance of this alignment occurring randomly is less than 1%. Something in the earliest epochs of the universe must have influenced not just where these quasars formed, but how they spin. This force or property of space-time operated on scales far larger than current theories predict is possible. This conclusion was not reached easily. Measuring the rotation axis of a quasar billions of light years away presents enormous technical challenges. Scientists couldn't observe the rotation directly. Instead, they measured the polarization of light from each quasar. Of the 93 quasars studied, 19 showed significant polarization signals. By analyzing this polarized light and combining it with other data, researchers could determine the angle of each quasar's accretion disk and, consequently, the direction of its spin axis. The results painted a picture of cosmic organization that extends far beyond what we thought possible. When a quasar sits within one of the universe's great filaments, its spin axis tends to point along that filament. This alignment suggests that the cosmic web, typically thought to influence only the distribution of matter in the universe, somehow also shapes the way that matter moves and rotates. This discovery joins other puzzling large-scale features that challenge our understanding of cosmic evolution. The implications ripple through multiple fields of physics and cosmology. If some unknown mechanism can influence the rotation of black holes across billions of light years, what does this tell us about the nature of space and time? What forces were at work in the early universe that could impart such large-scale organization? Some theorists suggest these alignments might be fossils from the universe's earliest moments, remnants of quantum fluctuations stretched to cosmic scales by inflation, the theorized period of rapid expansion immediately after the Big Bang. Others propose that exotic forms of matter or energy might be responsible, or that our understanding of gravity itself might need revision. The finding becomes even more significant when we consider that the quasars we observe are actually showing us the universe as it existed billions of years ago, when it was much younger. The light from these distant objects has traveled so far that we see them as they were in the cosmic past. This means whatever caused these alignments must have been present in the universe's youth, perhaps even encoded in its earliest moments. The discovery also raises questions about cosmic evolution. Supermassive black holes are thought to grow through a series of chaotic events, merging with other black holes and consuming matter from random directions. The process should randomize their spin orientations. The fact that we observe alignment instead suggests either that the initial conditions of their formation were somehow coordinated, or that some ongoing process maintains this alignment against the chaos of cosmic evolution. As our instruments and techniques improve, astronomers continue to study these aligned quasars, searching for clues that might explain their synchronized dance. Each new observation adds detail to the picture, while also raising new questions about the fundamental nature of our universe. In their alignment, these ancient cosmic beacons remind us that even after centuries of scientific progress, the universe still holds deep mysteries that our current theories cannot explain. According to quantum mechanics, the emptiest regions of space are anything but empty. What we think of as pure vacuum seethes with an invisible energy that permeates every fraction of the cosmos. This vacuum energy represents one of the most perplexing mysteries in modern physics, where theory and observation clash in spectacular fashion. The mathematics of quantum physics tells us that space itself is filled with countless virtual particles popping in and out of existence. These particles appear in pairs, flashing briefly into reality, before annihilating each other in a cosmic dance that occurs everywhere, all the time. Even in the coldest, darkest void between galaxies, this quantum froth bubbles with activity. We can actually observe the effects of this vacuum energy in laboratories. When scientists place two metal plates extremely close together, about 1,000 nanometers apart, these plates experience a tiny but measurable attractive force. This phenomenon, known as the Casimir effect, occurs because the narrow gap between the plates restricts which virtual particles can appear there, creating an imbalance in the vacuum energy that pushes the plates together. Vacuum energy also manifests in other subtle ways. It causes atoms to spontaneously emit light, creates tiny shifts in the energy levels of hydrogen atoms, known as the Lamb shift, and might even cause black holes to slowly evaporate through a process proposed by Stephen Hawking. These effects have been measured with extraordinary precision, confirming that vacuum energy is as real as the chair you sit in or the air you breathe. But here is where the mystery deepens. When physicists calculate how much vacuum energy should exist in a given volume of space, they arrive at an astronomical number, 10 to the power of 113 joules per cubic meter. This amount of energy would be enough to instantly vaporize any matter in the universe. Yet when astronomers observe the cosmos, they find that the actual vacuum energy must be drastically smaller, closer to 10 to the negative 9th joules per cubic meter. This discrepancy between theory and observation spans an almost incomprehensible 122 orders of magnitude. It represents the largest disagreement between prediction and measurement in all of science. Imagine predicting the depth of a swimming pool and being off by an amount larger than the size of the observable universe. This vast mismatch has been dubbed the vacuum catastrophe. The implications of this problem ripple through our entire understanding of physics. Vacuum energy should, according to Einstein's theory of general relativity, act as a kind of anti-gravity, pushing space itself apart. Indeed, astronomers have discovered that our universe is expanding at an accelerating rate, apparently driven by what we call dark energy. But the amount of dark energy we observe is far too small to match our calculations of vacuum energy. Some physicists propose that there might be some unknown mechanism that almost perfectly cancels out most of the vacuum energy, leaving behind only the tiny amount we observe. Others suggest our theories of quantum mechanics or gravity might need fundamental revision. Still, others wonder if we might be thinking about the problem entirely wrong, and that some completely new physics awaits discovery. The mystery extends into the earliest moments of our universe. During the period of cosmic inflation, just after the Big Bang, vacuum energy may have played a crucial role in driving the exponential expansion of space. Understanding vacuum energy could therefore help us understand not just the present state of the cosmos, but its very beginning. This quantum vacuum also challenges our intuitive understanding of nothingness. The idea of truly empty space turns out to be impossible in quantum mechanics. The uncertainty principle, one of the fundamental rules of quantum physics, requires that energy and time remain uncertain at very small scales. This uncertainty manifests as an unavoidable minimum energy present everywhere in space. The effects of vacuum energy might even influence the future of the universe. If vacuum energy remains constant as space expands, it would eventually overwhelm all other forms of energy and matter. The cosmos would continue accelerating in its expansion forever, possibly ending in what physicists call the Big Rip, where even atoms would be torn apart by the tremendous expansion of space itself. Experimental physicists continue to devise increasingly precise measurements of vacuum energy's effects, while theoretical physicists propose new ideas to resolve the vacuum catastrophe. Some suggest connections to string theory, which predicts additional spatial dimensions that might help explain the disparity. Others explore modifications to quantum field theory or seek ways to link vacuum energy to the mysteries of dark matter. Understanding vacuum energy may also have practical implications. Some researchers speculate that if we could somehow tap into the enormous reservoir of vacuum energy, it could provide a virtually unlimited power source. However, most physicists consider this unlikely, as extracting useful energy from the vacuum would require technology far beyond our current capabilities. The puzzle of vacuum energy reminds us that even empty space, the simplest possible thing we can imagine, holds deep mysteries that continue to challenge our most fundamental theories about the nature of reality. In the seeming nothingness between everything, we find one of the universe's greatest enigmas. High above and below the heart of our Milky Way galaxy loom two colossal structures that should not exist. Discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, these vast bubbles of high-energy radiation stretch out into intergalactic space, spanning a distance of 50,000 light-years, nearly half the diameter of our entire galaxy. The Fermi bubbles, as they are now known, are invisible to the human eye but blaze brilliantly in gamma-ray light, the most energetic form of radiation in the universe. These enormous lobes of energy rise like ghostly wings from the galactic center, their edges sharply defined against the cosmic background, suggesting they were created by a single dramatic event in our galaxy's history. What makes these structures particularly puzzling is their symmetry. The bubbles extend equal distances both above and below the galactic plane, suggesting they originated from a powerful eruption at the galaxy's core. At their center lies our galaxy's supermassive black hole, an object 4 million times more massive than our Sun. While this black hole is relatively quiet today, The Fermi bubbles may be echoes of a more violent past. The radiation from these bubbles is remarkably uniform and distinct from the rest of our galaxy. While the Milky Way's disk glows in gamma rays from the interaction of cosmic rays with gas and dust, the bubbles emit radiation at even higher energies. This suggests they are filled with extremely energetic particles, accelerated by some tremendous force to nearly the speed of light. Scientists have proposed several theories to explain these enigmatic structures. The leading hypothesis suggests that several million years ago, our galaxy's central black hole underwent a period of intense feeding activity. As matter fell toward the black hole, it would have been heated to extreme temperatures, and some of it blasted back into space in the form of powerful jets perpendicular to the galactic disk. These jets could have inflated the bubbles we see today, much like cosmic balloons. Another possibility is that the bubbles were created by a period of intense star formation near the galactic center. When massive stars explode as supernovae, they create powerful winds that can blow huge bubbles in the surrounding gas. A burst of star formation could have triggered enough supernovae to generate these galactic-scale structures. However, this scenario struggles to explain the bubble's sharp edges and uniform appearance. The true nature of these bubbles becomes even more intriguing when we consider their contents. The gamma rays we observe are produced when extremely energetic particles collide with lower energy radiation, suggesting the bubbles are filled with a plasma of high-energy particles trapped by magnetic fields. These particles appear to have been accelerated to energies far beyond what we can achieve in our most powerful particle accelerators on Earth. The discovery of the Fermi bubbles was completely unexpected. They remained hidden from view until sophisticated analysis techniques revealed their presence in Fermi's data. This raises an exciting possibility. What other cosmic structures might be waiting to be discovered? Indeed, in Fermi's most recent catalog of gamma-ray sources, fully 1/3 of the detected emissions come from locations with no known gamma-ray producing objects. The bubbles also provide a unique laboratory for studying the interaction between supermassive black holes and their host galaxies. While we observe powerful jets from black holes in other galaxies, the Fermi bubbles offer an unprecedented close-up view of such structures. Their study could help us understand how black holes influence galactic evolution and how they transfer energy into their surroundings. Timescales pose another mystery. If the bubbles were indeed created by our central black hole, the event that formed them must have occurred relatively recently in cosmic terms, perhaps just a few million years ago. This suggests our galaxy's center, which appears relatively peaceful today, may be merely resting between episodes of intense activity. We might be witnessing the aftermath of our galaxy's most recent energetic outburst. The magnetic fields that shape and contain the bubbles present their own puzzles. These fields must be extraordinarily stable to maintain the bubble's sharp edges over millions of years, yet flexible enough to allow the structures to expand to their current size. Understanding how these fields work could provide new insights into cosmic magnetism on the largest scales. As telescopes continue to observe these structures across different wavelengths of light, new details emerge. Recent observations have revealed that the bubbles contain multiple layers and complex internal structures. These features might preserve a record of multiple explosive events or reflect the influence of the galaxy's rotation on their evolution. The Fermi bubbles remind us that even our own cosmic backyard holds profound mysteries. They stand as enormous question marks written in gamma rays across our galaxy, challenging our understanding of black holes, cosmic rays, and the dynamic life of galaxies. Their continued study promises to reveal new insights about the dramatic forces that shape our cosmic home. In the cosmic darkness, brief flashes of radio energy pierce through space, each lasting mere milliseconds yet bearing the energy our Sun produces in an entire year. These fast radio bursts, or FRBs, represent one of modern astronomy's most perplexing phenomena, combining incredible power with precise patterns that seem to hint at underlying laws we have yet to understand. First discovered in 2007, these cosmic flashes arrive from galaxies billions of light-years away. Each burst contains radio waves that sweep from higher to lower frequencies as they arrive, a pattern that tells us they have traveled through the thin gas that fills intergalactic space. This frequency sweep acts like a cosmic yardstick, allowing astronomers to measure vast distances across the universe. The bursts divide themselves into two distinct categories. Most FRBs flash once and never appear again, their sources falling silent after their singular cosmic shout. But others, called repeaters, send multiple signals from the same location in space. These repeating bursts have transformed our understanding of the phenomenon, allowing astronomers to study patterns that might reveal their origin. One such repeater, designated FRB 22200912A, has recently displayed behavior never seen before. Observed by the Allen Telescope Array in California, this source produced 35 separate bursts over 2 months. While all repeating FRBs show a characteristic drift from higher to lower frequencies, this one revealed an additional pattern. The central frequency of each burst gradually decreased over time, creating what scientists describe as a cosmic slide whistle when converted to sound. This discovery highlights how much we still have to learn about these events. Current theories suggest that at least some FRBs originate from magnetars. These stellar remnants possess magnetic fields so powerful they would tear apart atoms if brought within 1,000 kilometers of Earth. Other proposed sources include the collision of neutron stars, the merger of white dwarf stars, or exotic phenomena involving hypothetical cosmic strings. Each theory explains some aspects of FRBs, but struggles to account for all their observed properties. The varying patterns between different sources suggest we might be seeing multiple types of cosmic events that produce similar signals. The precision of these bursts particularly puzzles astronomers. Despite lasting only thousandths of a second, the radio waves within each burst arrive in precise frequency patterns. It's as if someone is playing a perfectly timed musical scale that descends through specific notes, but playing it faster than any human musician could manage. The amount of energy contained in these bursts defies easy explanation. In less time than it takes to blink, a single FRB releases more energy than our Sun produces in 365 days. Yet whatever creates them must be able to reset and repeat this process in some cases, ruling out any mechanism that would destroy the source. Modern radio telescopes continue to detect more of these events, with thousands now recorded. This growing catalog reveals patterns that both illuminate and deepen the mystery. Some repeating sources show regular periods of activity followed by silence, while others appear completely random. Some bursts contain multiple subpulses, like cosmic stutters, while others arrive as clean, single pulses of radio energy. The discovery of a repeating FRB within our own Milky Way galaxy in 2020 provided new clues. This burst came from a known magnetar, supporting the theory that these highly magnetic neutron stars play a role in creating FRBs. However, this nearby burst appeared much weaker than the ones we detect from other galaxies, suggesting we might be seeing different stages or types of similar events. Scientists have begun using FRBs as tools to study the universe, even while their origin remains unclear. The way their radio waves are distorted by intergalactic material helps map the distribution of matter between galaxies. Their brief, bright signals might one day serve as cosmic lighthouses, helping us understand the structure and evolution of the universe. The continuing mystery of fast radio bursts reminds us that the universe still holds fundamental secrets. These precisely tuned cosmic whistles, powerful enough to be detected across billions of light years, yet brief enough to be missed in a moment's distraction, represent phenomena pushing the boundaries of known physics. Their study continues to reveal new patterns and pose new questions, suggesting we have much yet to learn about the most energetic events in our cosmos. As our telescopes grow more sensitive and our monitoring more constant, each new discovery about fast radio bursts seems to add layers to their mystery. They remain a cosmic puzzle that combines profound questions about the laws of physics with the promise of new insights into the structure and behavior of our universe. Throughout the cosmos, pairs of dead stars perform a fatal dance. These binary systems, containing neutron stars or black holes, spiral ever closer together in an orbital waltz that will end in cosmic catastrophe. As they draw nearer, their immense gravitational fields generate ripples in the fabric of spacetime itself, sending gravitational waves radiating across the universe. These death spirals take many forms. Some involve white dwarfs, the dense remnants of stars like our Sun, while others pair even more extreme objects like neutron stars or black holes. In 2021, astronomers discovered one such doomed couple just 1,500 light-years from Earth. The system, designated HD 265435, consists of a massive white dwarf and a smaller companion star locked in an orbit lasting just 100 minutes. The fate of this system is sealed by fundamental physics. As the stars orbit each other, they lose energy through gravitational waves, causing their orbits to decay. The more massive white dwarf's gravity gradually distorts its companion into a teardrop shape, pulling away material that will eventually trigger a catastrophic supernova explosion. Scientists calculate that in about 70 million years, these stars will merge in a blast visible across much of the galaxy. Even more dramatic are the death spirals of neutron stars, objects so dense that a teaspoon of their matter would weigh billions of tons. When two neutron stars spiral together, they create one of the most violent events known to science. In their final moments, they orbit each other hundreds of times per second, moving at nearly the speed of light. The gravitational waves they generate become so powerful they can be detected across billions of light years. The physics of these final moments challenges our understanding of nature itself. As the stars approach each other, their enormous gravitational fields warp space-time so extremely that our best computer models struggle to simulate what happens. The star's incredible density and rotation create magnetic fields trillions of times stronger than Earth's, while their surface gravity is strong enough to distort the very atoms they're made of. The actual merger occurs in mere milliseconds. When the stars finally collide, they create conditions more extreme than anywhere else in the universe except the Big Bang itself. Temperatures soar to hundreds of billions of degrees, and densities reach levels where the distinction between normal matter and pure energy begins to blur. These conditions are so extreme that they forge the heaviest elements in the universe, including gold and platinum. The aftermath of such mergers produces multiple signals across the electromagnetic spectrum. Astronomers first confirmed this in 2017 when they detected gravitational waves from a neutron star merger followed by a short gamma-ray burst and then a longer lasting glow called a kilonova. This single event revealed how most of Earth's precious metals were created and confirmed theories about the origin of certain mysterious explosions that had puzzled scientists for decades. Black hole mergers represent the most extreme version of these cosmic death spirals. As two black holes orbit each other, they create such powerful distortions in spacetime that light itself follows twisted paths around them. The gravitational waves they generate in their final plunge carry away more energy in a few seconds than all the stars in the visible universe produce in the same time. Yet, for all their violence, these death spirals play a crucial role in cosmic evolution. The heavy elements forged in neutron star mergers become part of the gas clouds that will form new stars and planets. The gravitational waves they generate provide astronomers with a new way to observe the universe, allowing us to detect events that would otherwise remain invisible. Scientists continue to discover new varieties of these fatal dances. Some systems contain stars of dramatically different masses, leading to complex orbital dynamics. Others involve three or more objects, creating chaotic gravitational interactions that can eject stars at enormous speeds or cause them to collide sooner than expected. One particularly intriguing variety involves a white dwarf stealing material from its companion so gradually that it approaches the critical mass needed for explosion over millions of years. These systems serve as cosmic time bombs, appearing stable until the white dwarf crosses a threshold called the Chandrasekhar limit, about 1.4 times the mass of our Sun. At this point, the star's core collapses and triggers a Type 1a supernova, an explosion so consistent in its brightness that astronomers use it to measure vast cosmic distances. The study of binary star death spirals continues to yield surprises. Theoretical models that attempt to predict the gravitational waves from these events must account for effects from both Einstein's theory of relativity and quantum mechanics, two branches of physics that we still haven't fully reconciled. The extreme conditions created as the stars merge may offer clues about how to unite these fundamental theories. As our ability to detect gravitational waves improves, we continue to discover new details about these cosmic catastrophes. Each detection helps us understand how matter behaves under the most extreme conditions possible, while also revealing the violent processes that created the elements necessary for life itself. Deep within the spiral arms of galaxies lie vast clouds where stars are born. These stellar nurseries, spanning hundreds of light years, are cosmic forges where gravity, magnetism, and turbulence compete in an intricate dance that transforms clouds of gas and dust into blazing new suns. Yet despite their crucial role in the cosmic story, many aspects of how these stellar birthplaces function continue to puzzle astronomers. The process begins with enormous molecular clouds composed primarily of hydrogen and helium, along with traces of heavier elements forged by previous generations of stars. These clouds can contain enough material to create thousands or even millions of stars. But the journey from diffuse gas to newborn star is far from straightforward. Most of the cloud's material resists the pull of gravity, supported by complex magnetic fields that thread through the gas like invisible spider webs. These magnetic fields present one of the greatest challenges to our understanding. Theory suggests they should prevent most stars from forming, acting like a cosmic safety net that supports the gas against collapse. Yet clearly, stars do form, and in great numbers. Astronomers have observed that the magnetic fields somehow become twisted and tangled by turbulent motions within the cloud. But modeling exactly how this happens remains beyond our current computational capabilities. The turbulence itself adds another layer of mystery. Gas within stellar nurseries moves in chaotic flows, creating swirls and eddies at all scales, from sizes smaller than our solar system to larger than whole star clusters. These movements can either prevent star formation by disrupting collapsing clouds, or encourage it by creating dense regions where gravity can overcome other forces. Predicting which outcome will occur in any given region has proven extraordinarily difficult. The Orion Nebula offers our closest view of these processes in action. Located just 1,500 light-years from Earth, this stellar nursery reveals its secrets through an array of telescopes observing at different wavelengths. Within its glowing gases, astronomers have identified hundreds of protostellar cores, regions where the collapse towards stellar birth has begun. Yet even here, with such a clear view, fundamental questions remain about why some regions of the cloud form stars, while others do not. Temperature adds another variable to this cosmic equation. The gas in stellar nurseries ranges from a frigid -400 degrees Fahrenheit in the densest regions to several thousand degrees in areas heated by nearby young stars. These temperature variations affect how the gas moves and responds to magnetic fields, creating feedback loops that can either enhance or suppress star formation. Recent observations have revealed that stellar nurseries are far more dynamic than once thought. Rather than being isolated clouds quietly forming stars, they interact with their surroundings through powerful outflows and radiation from newly formed stars. These interactions can trigger the formation of new stars in some regions, while dispersing the gas needed for star formation in others. The role of rotation presents yet another puzzle. As gas clouds collapse to form stars, conservation of angular momentum should cause them to spin faster, much like an ice skater pulling in their arms. This rotation should prevent material from reaching the forming star. While astronomers have observed disk-like structures around young stars that appear to solve part of this problem, the exact mechanism by which clouds shed their rotation remains unclear. Modern telescopes have revealed intricate structures within stellar nurseries that challenge our understanding. The famous pillars of creation in the Eagle Nebula show how radiation from nearby massive stars sculpts the gas into towering columns. Within these columns, dense globules of gas appear poised to form new stars, yet our models cannot reliably predict which will successfully birth stars and which will dissipate back into the nebula. The chemical composition of stellar nurseries adds further complexity. While primarily composed of hydrogen and helium, these clouds contain small amounts of more complex molecules, some of them organic. These molecules affect how the gas cools and collapses, but tracking their influence through the star formation process requires computational power beyond our current capabilities. Perhaps most puzzling is the question of efficiency. Observations show that only about 1 to 10% of the gas in a typical molecular cloud ends up in stars. Our best theoretical models struggle to explain why star formation is so inefficient, suggesting we are missing some crucial physics in our understanding of how stellar nurseries operate. The birth of massive stars poses particular challenges to our models. These cosmic giants, more than 10 times the mass of our Sun, should theoretically prevent their own formation through the intense radiation they generate while still growing. Yet, they clearly exist, suggesting our understanding of how gas flows onto forming stars remains incomplete. As we develop more powerful telescopes and more sophisticated computer models, we continue to uncover new aspects of these stellar birthplaces. Each discovery brings us closer to understanding the complex interplay of forces that transform cosmic gas into new stars, while also revealing just how much remains to be learned about these fundamental cosmic processes. At the hearts of certain galaxies lurk monsters that defy explanation. These ultramassive black holes, containing more than 10 billion times the mass of our Sun, push the boundaries of what we thought possible in cosmic evolution. The largest known example, Phoenix A, sits 5.8 billion light-years away at the center of the Phoenix galaxy cluster, containing the mass of 100 billion suns within its event horizon. To appreciate the scale of these objects, consider that the supermassive black hole at the center of our own Milky Way galaxy contains only about 4 million solar masses. Ultramassive black holes are not just larger versions of these more common cosmic objects. They are 10,000 times more massive on average, and their very existence poses fundamental questions about how such enormous concentrations of matter could have formed. The challenge lies in the time required to build such massive objects. Even if a black hole began growing shortly after the Big Bang and consumed material as fast as physically possible, it would struggle to reach such enormous masses through normal growth processes. The powerful radiation released by infalling matter creates intense pressure that pushes away additional material, creating a natural limit on how quickly a black hole can feed. Scientists have discovered that these cosmic titans tend to reside in the brightest galaxies at the centers of massive galaxy clusters. These locations make sense as they provide access to the most material for growth. But even the rich environment of a galaxy cluster cannot easily explain their extreme masses. Some other mechanism must be at work. Recent research suggests that these objects may impose their own growth limits through a cosmic feedback loop. As gas falls toward an ultramassive black hole, not all of it reaches the event horizon. The portion that doesn't make it in gets blasted back out in powerful jets that extend far beyond their host galaxies. These jets heat surrounding gas and push it away from the galaxy's central region, effectively cutting off the black hole's food supply. This self-limiting behavior leads scientists to theorize that there may be a natural cap on how massive these objects can become. Current calculations suggest this limit lies around 100 billion solar masses. Intriguingly, this means we may have already discovered the largest possible ultramassive black hole in Phoenix A, which sits right at this theoretical limit. The origin of these objects remains one of astronomy's greatest puzzles. One possibility is that they formed from peculiar types of stars in the early universe. These first-generation stars, never directly observed but theoretically predicted, might have been hundreds or even thousands of times more massive than today's stars. When such stars collapsed, they could have created unusually large seed black holes that had a head start in growing to ultramassive size. Another theory suggests these giants formed through the merger of multiple supermassive black holes during the collisions of their host galaxies. We know galaxies frequently merge as the universe evolves, and their central black holes should eventually coalesce as well. However, this process alone struggles to explain the most extreme examples we observe, as it would require an unlikely number of precisely orchestrated mergers. The mystery deepens when we consider timing. Many ultramassive black holes appear to have reached their enormous sizes very early in the universe's history, when it was only a fraction of its current age. This rapid growth in the cosmic dawn challenges our understanding of how quickly black holes can accumulate matter, suggesting either that our theories of black hole feeding are incomplete or that some unknown mechanism accelerated their early growth. These cosmic behemoths don't just sit quietly in space. Their immense gravitational influence shapes the evolution of their host galaxies and even affects the larger galaxy clusters around them. The powerful jets they produce can prevent gas from cooling and forming new stars across vast regions of space, effectively controlling the rate of star formation in their vicinity. Recent observations using the most powerful telescopes have revealed that ultramassive black holes might be more common than previously thought. They appear to follow a pattern, with their masses correlating strongly with the total stellar mass of their host galaxies. This relationship suggests a deep connection between how black holes grow and how galaxies evolve, though the exact nature of this connection remains unclear. Scientists continue searching for even larger examples, though if the theoretical mass limit proves correct, they may not find any black holes substantially more massive than Phoenix A. However, studying the ones we know about may help solve other cosmic mysteries, such as how galaxies formed in the early universe and how the largest structures in the cosmos came to be. Understanding these extraordinary objects pushes us to the limits of our knowledge about gravity, space, and time. Their existence reminds us that the universe can assemble structures more massive and extreme than we ever imagined possible, while their properties continue to challenge our theories about how the cosmos works. Imagine looking down at our galaxy from above, watching as billions of stars dance in a cosmic spiral. But there's something else there. Something that shouldn't exist according to our earliest models of galaxy formation. A massive bar of stars, gas, and dust, stretching across thousands of light years through the very heart of the Milky Way. This isn't a rare cosmic accident. Across the universe, about 2/3 of all spiral galaxies harbor these mysterious bars, structures so common yet so puzzling that they've become one of astronomy's most intriguing mysteries. These galactic bars are cosmic architects, sculptors of stellar destinies. Picture a bar as a giant cosmic paddle, spanning tens of thousands of light years, stirring the galaxy's contents like a celestial spoon in a cosmic coffee cup. But these aren't static structures. They're dynamic, evolving features that can dramatically reshape entire galaxies over billions of years. The mystery deepens when we look at how these bars form. Imagine a galaxy's stars as dancers in an enormous cosmic ballet. Over time, something remarkable happens. The dancers begin to synchronize their movements, creating a wave of stellar choreography that ripples outward from the galaxy's center. This density wave, as astronomers call it, gradually reshapes the orbits of countless stars, bending their paths until they fall into lockstep, forming the bar we see today. But here's where things get truly strange. These bars aren't just passive features, they're cosmic nurseries. As the bar rotates, it acts like a giant funnel, channeling vast rivers of gas and dust from the outer spiral arms toward the galaxy's center. This process triggers the birth of new stars, creating brilliant stellar nurseries that light up the galactic core. It's a process so efficient that it can even feed the supermassive black holes lurking at the centers of these galaxies, triggering what astronomers call active galactic nuclei. Yet the very success of these bars contains the seeds of their own destruction. As they channel more and more matter toward the galaxy's center, they grow larger and more massive. But there's a catch, a cosmic limit to how much mass they can accumulate before something extraordinary happens. When this limit is reached, the bar experiences what astronomers call a buckling event, a cosmic convulsion where the entire structure becomes unstable and begins to collapse inward. During this buckling, the bar doesn't just disappear, it transforms. Imagine a rubber band being compressed from both ends. The bar becomes shorter and thicker, changing the galaxy's appearance and altering the orbits of countless stars. Even the presence of a supermassive black hole at the galaxy's center, with its immense gravitational pull, can't prevent this transformation, though it can delay the inevitable. Perhaps most fascinating is that this isn't a one-time event. Astronomers now believe these bars are recurring phenomena, part of a cosmic cycle that takes about 2 billion years to complete. Like a phoenix rising from its ashes, new bars can form after old ones decay, each iteration writing a new chapter in the galaxy's evolution. This cycle tells us something profound about galaxy evolution. Recent studies have revealed that only 20% of spiral galaxies in the distant past had bars, compared to 65% of nearby galaxies today. This suggests that bars are signs of galactic maturity, marking the end of a galaxy's formative years and the beginning of its adult life. Consider our own Milky Way's bar, a structure so massive it influences the motion of stars across tens of thousands of light years. Yet we're still uncovering its secrets. Recent observations have shown that our galaxy's bar isn't just a simple rod of stars. It's a complex structure that may even be causing our galaxy's spiral arms to twist and writhe in unexpected ways. The existence of these bars challenges our understanding of galaxy formation and evolution. Early universe models suggested that galaxies shouldn't be stable enough to form bars until relatively recently. Yet astronomers have discovered barred spirals far back in time, forcing us to rethink our theories about how galaxies evolve. The mystery of bar instability touches on one of the most fundamental questions in astronomy. How do galaxies, these vast cities of stars, change and evolve over cosmic time? The bars we observe are like cosmic fingerprints, each one telling a story of galactic evolution, stellar birth, and the intricate dance of gravity across unimaginable distances. As we peer deeper into space, looking further back in time, we're beginning to understand that these bars aren't just structural features, they're timekeepers of galactic evolution, markers of cosmic maturity, and architects of stellar destinies. Yet for all we've learned, the fundamental physics driving their formation, evolution, and destruction remains one of the great mysteries of the cosmos, a reminder that even the most common features of our universe can hold profound secrets. In the empty darkness between galaxies, invisible forces stretch across millions of light years. These are the primordial magnetic fields, cosmic remnants from the universe's earliest moments, still influencing the cosmos today. Before the first stars ignited, before atoms existed, these mysterious magnetic fields emerged from the chaos of creation. The discovery of these ancient fields challenges everything we thought we knew about the early universe. In the beginning, when the cosmos was a hot soup of electrons and protons, something extraordinary happened. The motion of these charged particles generated the first magnetic fields in existence. As simple as this might sound, it opened the door to one of astronomy's greatest mysteries. These fields are incredibly weak, measuring between 10 to the negative 16th and 10 to the negative 9th Gauss. For comparison, Earth's magnetic field is about 1 Gauss. Yet despite their weakness, these primordial fields stretch across incredible distances. Scientists have detected them spanning 10 million light-years through the cosmic web of matter connecting galaxy clusters. The existence of these magnetic fields was first proposed by Ted Harrison in 1973. He realized that the early universe's plasma state provided perfect conditions for magnetic fields to arise. Later research suggested other possible origins. When the universe cooled enough for the electromagnetic force to separate from the weak nuclear force, this cosmic phase transition could have sparked the first magnetic fields. One of the most compelling pieces of evidence for these ancient fields comes from the vast empty regions between galaxies. In these galactic filaments, where no stars or galaxies exist to generate magnetic fields, scientists have detected magnetic energy stretching across enormous distances. The team led by Federica Govoni at the National Institute for Astrophysics found conclusive evidence of magnetic fields in these supposedly empty spaces. These primordial fields reveal themselves through several cosmic signatures. When light from distant blazars, powerful jets from supermassive black holes, travels through these magnetic fields, it becomes polarized. This effect, called Faraday rotation, allows astronomers to map these invisible fields across space. The fields also cause cosmic rays to curve in their paths, producing distinctive synchrotron radiation that we can detect with radio telescopes. The mystery of these fields might hold the key to solving one of modern cosmology's biggest puzzles, the Hubble tension. This apparent conflict between different measurements of the universe's expansion rate has troubled astronomers for years. Scientists Levon Pogosyan and Karsten Yadamzik discovered that including primordial magnetic fields in our models helps resolve this contradiction. These ancient fields would have influenced how matter clumped together in the early universe. Along magnetic field lines, plasma would gather at weak points, leading to earlier formation of hydrogen than previously thought. This seemingly small change cascades through cosmic history, affecting how we interpret the size and distance of objects in the distant universe. The impact of these fields extends far beyond theoretical physics. When powerful gamma rays from distant black holes pass through regions containing primordial magnetic fields, they interact differently with intergalactic material. Some gamma rays never reach Earth, blocked by the complex interaction between the magnetic fields and particle physics. This effect allows astronomers to measure the strength of these ancient fields by studying what light makes it to our telescopes. Research using the Fermi telescope has revealed subtle blurring effects in the jets from supermassive black holes, providing another line of evidence for these cosmic magnetic fields. A team led by Shinichiro Ando and Alexander Kusenko analyzed 170 black hole images, finding deviations that suggest the presence of primordial magnetic fields throughout space. Fast radio bursts, mysterious flashes of radio waves from distant galaxies, offer yet another window into these ancient magnetic fields. As these bursts travel through space, the magnetic fields alter their properties in measurable ways. By studying these alterations at different frequencies, astronomers can map the structure of magnetic fields across vast cosmic distances. Perhaps most intriguingly, these fields might have played a crucial role in the formation of the first structures in the universe. Like gravity, magnetic fields can work across vast distances, helping to shape the distribution of matter in the cosmos. Understanding these primordial fields could reveal how the first galaxies and galaxy clusters came to be. The quest to understand primordial magnetic fields continues to drive new discoveries in cosmology. Their existence bridges the gap between the quantum realm of particle physics and the cosmic scale of galaxy formation. As we peer deeper into space and further back in time, these ancient magnetic fields remain one of the most profound and persistent mysteries of our universe. Deep in the quantum realm, a peculiar form of matter defies our basic understanding of time itself. Time crystals break the rules we thought governed the universe, creating repeating patterns that cycle endlessly without consuming energy. While regular crystals show symmetry in space, with atoms arranged in repeating grids, time crystals achieve something far stranger. They create symmetry in time. The concept emerged from theoretical physics, suggesting that matter could enter a state where it cycles through patterns like clockwork, returning to its original configuration again and again. Unlike a swinging pendulum that eventually stops, or a heart that requires energy to beat, these quantum structures theoretically maintain their rhythm indefinitely without any external input. Scientists first created time crystals in laboratories using quantum computers in 2016. They manipulated chains of ions using precision lasers, creating systems where the particles flip between quantum states in a perfect endless cycle. These laboratory time crystals demonstrate that matter can spontaneously organize itself in time, just as traditional crystals organize themselves in space. The quantum nature of time crystals makes them particularly fascinating. In quantum mechanics, particles can exist in multiple states simultaneously until measured. Time crystals harness this quantum superposition, creating systems where particles collectively flip between states in a coordinated dance. This quantum coherence allows the system to maintain its rhythm without degrading. What makes time crystals truly remarkable is their apparent violation of a fundamental physics principle, the second law of thermodynamics. This law states that systems naturally tend toward increasing disorder over time. Time crystals seem to resist this tendency, maintaining their ordered oscillations without dissolving into chaos. They achieve this by existing in their lowest possible energy state while still maintaining motion. The implications for deep space are profound. If time crystals can exist naturally in the cosmos, they would represent an entirely new state of matter, one that could survive the harsh conditions of space indefinitely. Their unique properties might allow them to preserve quantum information over vast periods, making them potential cosmic time capsules of quantum states. In the context of space-time, these structures raise intriguing possibilities. General relativity tells us that space and time are woven together into a single fabric. time crystals suggest that this fabric might have properties we never imagined, including the ability to support stable, repeating patterns in its temporal dimension. The search for natural time crystals in space presents unique challenges. Their quantum nature makes them difficult to detect at astronomical distances, and we are still developing the tools and methods needed to identify their signatures. Scientists theorize that extreme conditions near neutron stars or in the vicinity of black holes might provide the environment needed for time crystals to form naturally. Current laboratory experiments with time crystals require careful control of quantum systems. Scientists use ultra-cold temperatures and precise laser pulses to create the conditions necessary for time crystals to emerge. In one experiment, researchers used nitrogen vacancy centers in diamond, creating a system where electron spins flip in perfect synchronization without energy input. The connection between time crystals and quantum computing offers another avenue for exploration. Time crystals maintain stable quantum states longer than typical quantum systems, potentially providing new ways to store and process quantum information. This stability could be crucial for developing quantum computers capable of operating in the harsh environment of space. Recent experiments have revealed that time crystals can exist in connected systems, where multiple time crystals interact and influence each other. This discovery suggests the possibility of complex networks of time crystals, each maintaining their own rhythm while affecting their neighbors through quantum entanglement. The role of time crystals in cosmology remains largely theoretical. Some physicists propose that time crystals might have formed in the early universe, potentially influencing the development of cosmic structures we observe today. Their ability to maintain stable oscillations without energy input could have provided a mechanism for preserving quantum information through the chaotic conditions following the Big Bang. Understanding time crystals requires grappling with concepts that challenge our classical intuition. They represent a form of matter that exists not just in space, but in time itself, maintaining order through quantum mechanics rather than conventional forces. Their discovery has opened new questions about the nature of time, matter, and the fundamental symmetries that govern our universe. The study of time crystals continues to advance through both theoretical work and laboratory experiments. Each new discovery reveals more about how matter can organize itself in time and space, pushing the boundaries of our understanding of quantum mechanics and its role in the cosmos. In the vast darkness of space, particles with impossible energies slam into Earth's atmosphere. These cosmic rays pack the punch of a Major League fastball concentrated into a single atomic nucleus, making them the most energetic particles ever detected in the universe. Their existence poses one of astronomy's most perplexing mysteries. These ultra-high energy cosmic rays are not gentle visitors. When they collide with our atmosphere, they create spectacular cascades of secondary particles and flashes of light that scientists can detect from the ground. Each collision tells the story of a particle that has journeyed across unimaginable distances, carrying more energy than we can create in even our most powerful particle accelerators. The mystery deepened when scientists using the telescope array in Utah's desert discovered something extraordinary. A hotspot in the sky near the Big Dipper, where many of these powerful cosmic rays seem to originate. This region spans 40 degrees of the northern sky, an area 80 times larger than the full moon. Within this cosmic neighborhood, Something unknown is accelerating particles to energies exceeding a billion electron volts. But tracking these particles back to their source presents a unique challenge. As they travel through space, magnetic fields bend their paths. These cosmic railways twist and turn the particles, making it impossible to simply trace their trajectories back to their origins. It's like trying to determine where a leaf came from after it has been caught in multiple whirlwinds. The particles themselves are surprisingly simple. They are atomic nuclei, the cores of atoms stripped of their electrons, hurtling through space at nearly the speed of light. Most cosmic rays come from relatively nearby sources, like our Sun or exploding stars within our galaxy. But these ultra-high energy particles are different. They come from far beyond our galaxy, and their extreme energies suggest they must originate from some of the most violent events in the universe. Scientists have several suspects for these cosmic particle accelerators. Jets of matter spewing from violently exploding stars could provide the necessary energy. Even more promising are the enormous jets discharged by supermassive black holes at the centers of distant galaxies. These cosmic giants can create conditions far more extreme than anything we can reproduce on Earth. The Pierre Auger Gamma Ray Observatory in Argentina has joined the hunt, scanning the southern skies for similar patterns. They've found their own warm spot, suggesting multiple sources might exist across the cosmos. This discovery highlights the importance of studying the entire sky to unravel this cosmic puzzle. To detect these rare visitors from deep space, scientists use specialized equipment spread across vast areas. The telescope array in Utah watches for the telltale flashes of light created when cosmic rays crash into our atmosphere. These collisions occur high above the ground, protecting life on Earth from direct impacts while providing scientists with natural experiments in particle physics that would be impossible to recreate in any laboratory. The energy of these particles defies our current understanding of physics. The most powerful cosmic rays detected carry the energy of a fastball compressed into a single atomic nucleus. This concentration of energy is difficult to explain using known physical processes. Whatever creates these particles must be capable of acceleration far beyond what we thought possible. Scientists are expanding their detection arrays to gather more data. By increasing the size of these cosmic ray observatories, researchers hope to narrow down the search area from 40 degrees to just 5 degrees of sky. This precision would allow conventional telescopes to study specific objects within the hotspot, potentially revealing the cosmic accelerators responsible for these energetic particles. The hunt for the source of ultra-high energy cosmic rays connects multiple fields of physics. It combines our understanding of particle physics, magnetic fields, and the most extreme events in the universe. Each detection adds another piece to this cosmic puzzle, helping scientists understand how nature can accelerate particles to such extraordinary energies. These cosmic rays also serve as messengers from the distant universe. They carry information about the conditions in their source regions and the space they've traveled through. By studying their arrival directions, energies, and composition, scientists can probe environments far more extreme than anything we can create on Earth. The mystery of cosmic ray hotspots represents a frontier in our understanding of the universe. It challenges our theories about particle acceleration and forces us to consider new possibilities about the most energetic events in the cosmos. As detection technology improves and more data accumulates, we move closer to identifying the cosmic engines capable of launching these extraordinary particles across the vastness of space. The cosmos holds another bewildering secret. Huge clusters of galaxies containing thousands of stars and vast clouds of hot gas are moving together through space at nearly 2 million miles per hour. This coordinated cosmic dance, dubbed dark flow, points toward a mysterious force lurking beyond the edge of our observable universe. Scientists discovered this phenomenon while studying clusters of galaxies using the Wilkinson microwave anisotropy probe. By observing how these clusters interact with radiation left over from the Big Bang, researchers detected something extraordinary. Hundreds of galaxy clusters streaming in the same direction toward a point between the constellations Centaurus and Vela. This motion cannot be explained by any known gravitational forces within our observable universe. The observable universe includes everything we can theoretically see, stretching 13.7 billion light-years in all directions. This represents the distance light could have traveled since the Big Bang. But dark flow suggests something massive must exist beyond this cosmic horizon, tugging on the matter we can see. When astronomers first detected this flow, they studied 700 galaxy clusters reaching out to 6 billion light-years away, about half the distance to the edge of the observable universe. What stunned scientists was that the speed of this flow didn't decrease with distance. The clusters kept moving at the same rapid pace, regardless of how far away they were, defying our understanding of how gravity typically works. The implications are profound. Whatever is causing this motion must be truly enormous, potentially hundreds of billions of light-years away. These distances are so vast, they lie far beyond our observable universe, in regions of space-time we can never directly see. These regions might contain structures far larger than anything in our cosmic neighborhood. This discovery connects to a theory called inflation, which suggests our observable universe is just a tiny bubble in a much larger cosmos. During the universe's first fraction of a second, space expanded faster than light, pushing most of the cosmos far beyond our view. The dark flow could be evidence of massive structures that existed before this inflationary period. Their gravitational influence still felt across billions of light-years. These distant regions might be radically different from the universe we know. They may not contain stars or galaxies as we understand them. Instead, they could harbor massive structures or distortions in space-time itself, creating gravitational forces powerful enough to influence thousands of galaxy clusters across unfathomable distances. The discovery was made possible through the kinematic Sunyaev-Zeldovich effect, where X-rays from hot gas in galaxy clusters scatter photons in the cosmic microwave background radiation. This technical achievement allowed astronomers to measure the motion of clusters with unprecedented precision, revealing their coordinated movement through space. Dark flow adds another layer to our cosmic mysteries, joining dark matter and dark energy as phenomena that challenge our understanding of the universe. Unlike those other dark components, dark flow points to something specific: massive structures beyond our cosmic horizon, remnants perhaps of a time before the Big Bang itself. The finding suggests our observable universe might be like an island in a vast cosmic ocean. Just as someone standing on a beach can only see to the horizon, but knows the ocean continues beyond, we can only see to our cosmic horizon, while the universe likely extends far beyond. The dark flow acts like a current in this cosmic ocean, telling us about regions we cannot directly observe. Scientists continue to study this phenomenon, using increasingly sophisticated instruments to map the motions of galaxy clusters. Each observation adds to our understanding of this cosmic migration and what might be causing it. The evidence consistently points to something massive beyond our observable universe. What makes dark flow particularly intriguing is how it might help us probe the largest scales of existence. While we can never directly observe anything beyond our cosmic horizon, phenomena like dark flow provide clues about what lies beyond. They suggest our observable universe might be just one small part of a much larger, more complex cosmic structure. The mystery of dark flow forces us to confront the limitations of our perspective and the possibility that the cosmos is far stranger and more vast than we imagined. It reminds us that even with our most powerful instruments and advanced theories, the universe still holds secrets that lie just beyond our ability to directly observe. Around young stars, vast disks of gas and dust hold the building blocks of future solar systems. Within these protoplanetary disks, scientists have discovered something perplexing: distinct gaps and rings that challenge our understanding of how planets form. These cosmic clearings, once thought to be simple signatures of growing planets, tell a far more complex story. Recent observations using powerful telescopes like ALMA have revealed these gaps in stunning detail. The disks appear as cosmic bullseyes, with concentric rings separated by seemingly empty spaces. Initially, astronomers believed each gap marked the presence of a forming planet, sweeping its orbital path clean like a cosmic street sweeper. The reality has proven far more mysterious. Computer simulations tracking the evolution of these systems reveal an unstable cosmic dance. When scientists model 5 to 7 protoplanets within these disks, chaos emerges in just 40,000 years. This time span represents barely a moment in astronomical terms, far too brief for planets to carve out the stable gaps we observe in real systems. The mystery deepens when we consider planetary migration. Young planets don't stay in one place. They drift through their solar systems, pushed and pulled by gravitational forces and interactions with the surrounding disk. Some worlds may travel vast distances, making it impossible for them to maintain a clear orbital path. Earth itself likely wandered considerably during its formation, hidden within the disk, rather than revealing its presence through a visible gap. These findings force us to question our assumptions about planetary formation. The gaps we see might instead be created by orbital resonances, similar to how Jupiter's gravity helps maintain the asteroid belt in our solar system. A single large planet could potentially create multiple rings and gaps through its gravitational influence, without requiring the presence of other worlds. The temperature and density variations within these disks add another layer of complexity. Different regions might naturally form rings and gaps due to physical processes we don't yet fully understand. The interaction between gas and dust particles, the role of magnetic fields, and the effects of stellar radiation all contribute to shaping these disks in ways that can mimic the presence of planets. Particularly puzzling is the observation that some gaps contain visible protoplanets, while others remain empty despite similar appearances. This suggests that multiple mechanisms must be at work. A gap might be carved by a planet that later migrated elsewhere, maintained by gravitational resonances, or created by processes entirely unrelated to planet formation. The size and distribution of these gaps also present challenges. In many systems, They appear too numerous and too regularly spaced to be explained by planets alone. Our current models of planetary formation cannot account for so many worlds forming simultaneously while maintaining stable orbits. Yet, the gaps persist, hinting at fundamental processes we have yet to discover. These discoveries have important implications for our understanding of how planetary systems, including our own solar system, come into being. The presence of gaps doesn't necessarily indicate where planets will ultimately reside. A system's final architecture might bear little resemblance to the pattern of gaps in its youth. Young Earth-like planets prove particularly elusive in these observations. Rather than announcing their presence through clear gaps, these smaller worlds likely spend their formative years hidden within the disk's material. This means we might be missing crucial stages in the formation of planets similar to our own. Scientists continue to refine their models, incorporating new factors like the role of magnetic fields, radiation pressure, and complex gas dynamics. Each new observation adds another piece to this cosmic puzzle, revealing that planetary formation involves far more variables than previously thought. The gap mystery touches on one of astronomy's most fundamental questions. How do solar systems evolve from swirling disks of matter into organized systems of planets? The patterns we observe in these young systems suggest mechanisms at work that lie beyond our current understanding, driving home the complexity of cosmic birth. Our universe might be just a slice of something far bigger, like a sheet of paper floating in a thick book. This concept, called brain cosmology, emerges from string theory and offers a potential solution to one of physics' most persistent puzzles: why gravity appears so much weaker than all other forces in nature. The word brain comes from membrane, describing our entire universe as a three-dimensional surface embedded in a higher dimensional space called the bulk. Picture the bulk as an aquarium, and our universe as just one of several possible fish tanks within it. Everything we can observe, touch, or measure exists on our brain, except for one critical force: gravity. Unlike the electromagnetic force, the strong nuclear force, and the weak nuclear force, which remain trapped on our brain, gravity has the unique ability to leak into these extra dimensions. This leakage explains why gravity appears so weak in our observable universe. When you lift a small magnet and it pulls a paperclip against the entire gravitational force of Earth, you're witnessing this disparity in strength between electromagnetic and gravitational forces. Think of sound traveling through an apartment building. Within one apartment, you can hear sounds clearly, just as the electromagnetic force acts strongly within our brain. But sound also travels between apartments, growing fainter as it spreads through the building's structure, similar to how gravity spreads into the bulk, becoming weaker in our observable universe. The math behind brain cosmology suggests gravity should appear significantly stronger at very small scales, where less gravitational force has leaked away into the bulk. Scientists predict this effect would become noticeable at subatomic or submillimeter distances. Various experiments are currently underway to test this prediction, though no evidence has yet been found. This framework offers potential solutions to other cosmic mysteries. The cosmological constant, which describes the energy of empty space and drives the universe's acceleration, appears impossibly small compared to theoretical predictions. Brain cosmology with supersymmetry in the bulk might explain this discrepancy, as the extra dimensions could affect how this energy manifests in our observable universe. The history of these ideas stretches back to 1983. when scientists first proposed that ordinary particles might be confined to a subset of dimensions, while gravity experiences the full space. The concept gained significant momentum in 1998, when Merab Gogbarashvili showed how treating the universe as a thin shell expanding in five-dimensional space could solve the hierarchy problem of particle physics. In 1999, Lisa Randall and Raman Sundaram proposed two influential models of brane cosmology. Their work sparked intense interest in the field and led to numerous variations and extensions. One particularly intriguing proposal suggests our observable universe originated when two parallel branes collided, an idea known as the ekpyrotic theory. The implications of brane cosmology extend beyond theoretical physics. If correct, it would mean our universe is part of a larger multidimensional structure we can never directly observe. The extra dimensions would be just as real as length, width, and height, but impossible to perceive because all our observational tools, and even the particles they're made of, are confined to our brain. Consider dropping pebbles into a pond. The ripples spread out in 2 dimensions across the water's surface, much like how light and matter move through our brain. Fish living in the pond might never realize there's a 3rd dimension above and below them, just as we struggle to detect extra dimensions in the bulk. Recent observations have begun to constrain these theories. The Large Hadron Collider has searched for signs of gravity's enhanced strength at small scales. The detection of gravitational waves from merging neutron stars has allowed scientists to test how gravity behaves over vast distances. So far, these experiments have found no evidence for large extra dimensions, though they haven't ruled them out entirely. The mathematics underlying brane cosmology connects to other areas of theoretical physics. It relates to ideas about cosmic inflation, the nature of dark energy, and the possibility of other universes. The theory suggests that what we consider fundamental constants of nature might actually be consequences of our universe's position and properties as a brane within the larger bulk. If proven correct, brane cosmology would revolutionize our understanding of the cosmos. It would explain why gravity appears so weak, resolve inconsistencies in particle physics, and provide a framework for understanding the earliest moments of our universe. Until then, it remains one of physics' most elegant attempts to unite our understanding of the very large with the very small. Throughout the cosmos, ancient light performs a celestial time machine trick. Like sound bouncing off canyon walls, light from powerful cosmic events reflects off clouds of dust and gas, taking longer paths to reach Earth. These light echoes allow astronomers to witness explosive stellar events long after their initial flash has faded, providing unprecedented views of cosmic history. When powerful bursts of light strike interstellar dust clouds, the particles scatter and reflect the light in different directions. Some of this reflected light travels a more circuitous route to Earth, arriving years, centuries, or even millennia after the direct light from the original event. This delay creates a cosmic replay, allowing astronomers to study historical events as if they were happening now. The phenomenon is similar to what happens when lightning strikes during a thunderstorm. The initial flash reaches our eyes instantly, but the sound takes a longer path, arriving seconds later as thunder. In space, these light echoes can take thousands of years to reach us, bouncing off multiple dust clouds along the way, each reflection preserving information about the original event. Recent observations have revealed light echoes from supernovas that exploded centuries ago. As this ancient light continues its journey through space, it illuminates different portions of interstellar dust clouds, creating moving patterns of illumination that astronomers can track and study. These echoes contain spectral signatures that reveal the chemistry and physics of both the original event and the reflecting dust clouds. One of the most fascinating aspects of light echoes is their ability to provide multiple viewing angles of the same cosmic event. As light from an explosion travels outward in all directions, it encounters dust clouds at different distances and angles. When these reflections reach Earth, astronomers can essentially see the same event from different perspectives, something impossible with direct observation alone. The true power of light echoes lies in their ability to help astronomers study events that occurred before the invention of modern telescopes. Historical supernovas, stellar outbursts, and other cosmic explosions that occurred centuries ago can be studied in detail by analyzing their echoes. This allows scientists to verify and expand upon historical astronomical records, piecing together a more complete picture of our cosmic neighborhood's violent past. Scientists use sophisticated imaging techniques to detect and track these faint echoes. Because the reflected light is much dimmer than the original event, identifying genuine light echoes requires careful observation and analysis. Advanced telescopes and imaging systems must filter out other sources of light and movement to isolate these ancient signals. The dust clouds that create these echoes serve as natural cosmic mirrors, but they are far from perfect reflectors. Each reflection modifies the light slightly, encoding information about the dust's composition and structure. By studying how the light changes as it bounces off these clouds, astronomers can map the distribution and properties of interstellar matter between stars. Some light echoes remain mysterious, with no clear source event identified. These orphan echoes could be reflections of unknown stellar explosions, revealing cosmic events that occurred when humans were still in the Stone Age. Each such discovery adds another piece to our understanding of stellar evolution and the dynamic nature of our galaxy. The timing of light echoes provides valuable information about the three-dimensional structure of space. By measuring the delay between direct light and its echoes, astronomers can calculate the distances and positions of dust clouds with unprecedented accuracy. This helps create detailed maps of interstellar matter in our galaxy. The search continues for light echoes from different types of cosmic events. While supernovas provide the most dramatic examples, other phenomena like stellar mergers, gamma-ray bursts, and even events near supermassive black holes might leave detectable echoes. Each new discovery opens another window into the universe's past. Understanding light echoes requires precise measurements and complex calculations. Scientists must account for the movement of dust clouds, the evolution of the reflected light's spectrum, and the geometry of multiple reflection paths. This precision allows them to reconstruct events with remarkable accuracy, turning these cosmic mirrors into powerful tools for astronomical archaeology. These celestial time capsules continue to reveal new insights about the universe's history. As detection technology improves and more sky surveys catalog these phenomena, light echoes promise to illuminate ever more distant chapters in cosmic history, preserving the light of ancient celestial events for future astronomers to decode. In the outskirts of every spiral galaxy lies a profound mystery that challenges our understanding of physics. Stars at the edges of galaxies spin around their galactic centers far too quickly, defying the basic laws of gravity as we understand them. This galaxy rotation problem has led scientists to propose the existence of an invisible form of matter that holds our universe together. The story begins with astronomer Vera Rubin's pioneering observations in the 1970s. When studying spiral galaxies, she discovered something extraordinary. Stars at the outer edges were orbiting at nearly the same speeds as stars closer to the center. According to Newton's laws of gravity, this should be impossible. Just as planets farther from the Sun orbit more slowly, stars at a galaxy's edges should move much more slowly than those near the core. Think of a spinning figure skater. When they pull their arms in, they spin faster. When they extend their arms, they spin slower. This conservation of angular momentum should apply to galaxies too. The visible mass of a galaxy is concentrated in its center, so stars at the edges should orbit more slowly. But they don't. Instead, they maintain surprisingly high speeds, as if being pulled by something we cannot see. This led to the dark matter hypothesis. Astronomers proposed that galaxies must be embedded within massive halos of invisible matter. This dark matter doesn't interact with light or any other form of electromagnetic radiation, making it impossible to see directly. But its gravitational effects are unmistakable, providing the extra pull needed to explain the high orbital speeds of outer stars. The mathematics of this problem reveals something even more puzzling. Galaxy rotation curves, which show how orbital speed varies with distance from the center, follow remarkably consistent patterns across different galaxies. These curves become flat rather than declining as expected, suggesting dark matter must be distributed in very specific ways. The precision of these patterns hints at fundamental laws we don't yet understand. Dark matter halos appear to extend far beyond the visible edges of galaxies, containing several times more mass than all the visible stars, gas, and dust combined. Yet despite making up roughly 85% of all matter in the universe, dark matter remains one of science's most elusive mysteries. We can't see it, touch it, or directly detect it. We only know it exists because of its gravitational effects. Some scientists propose alternative explanations. Modified Newtonian dynamics, or MOND, suggests that gravity itself behaves differently at the extremely low accelerations found at galaxy edges. While this theory can explain some aspects of galaxy rotation, it struggles to account for other observations where dark matter appears necessary, such as the behavior of colliding galaxy clusters. The consistency of rotation patterns across different galaxies poses a particular challenge. If dark matter explains these patterns, why does it arrange itself in such similar ways across galaxies of different sizes and shapes? This hints at underlying physical laws governing dark matter's behavior that we have yet to discover. The problem becomes even more intriguing when studying different types of galaxies. From massive spiral galaxies like our Milky Way to smaller dwarf galaxies, the same patterns appear. The ratio of dark matter to visible matter seems to follow specific rules, suggesting a deep connection between visible and invisible matter that we don't yet comprehend. Advanced computer simulations attempt to model how dark matter halos form and evolve. These simulations suggest that dark matter should clump together in certain ways, creating a cosmic web that guides galaxy formation. However, some details of actual galaxy rotation curves still don't perfectly match these models, indicating gaps in our understanding. The search for dark matter particles continues in laboratories around the world. Scientists have built incredibly sensitive detectors deep underground, hoping to catch rare interactions between dark matter and normal matter. So far, these experiments have found no direct evidence of dark matter particles, deepening the mystery. The galaxy rotation problem represents one of the strongest pieces of evidence for dark matter's existence, yet it also reveals how much we still have to learn. The precise mathematical patterns observed in galaxy rotation curves suggest fundamental principles about the nature of matter and gravity that lie just beyond our current understanding. As our telescopes and instruments improve, astronomers continue to gather more detailed data about galaxy rotation. Each new observation adds to our knowledge, while simultaneously revealing new complexities in this cosmic puzzle. The solution may require new physics, new particles, or entirely new ways of thinking about the fundamental nature of our universe. Let's explore one of the strangest features ever discovered in space: mountains on neutron stars that are smaller than the height of a coffee cup. While this might sound tiny, the fact that these mountains exist at all challenges everything we know about gravity and matter. Think about how strong a neutron star's gravity is. A teaspoon of neutron star material would weigh billions of tons on Earth. This gravity is so intense that it should crush any bumps or irregularities flat, like a cosmic steamroller smoothing out the star's surface. Yet somehow these miniature mountains persist, defying the crushing force of gravity. To understand how remarkable this is, imagine shrinking Mount Everest down to the size of a grain of sand. Even at this tiny scale, such a mountain shouldn't be able to exist on a neutron star's surface. The gravity is so strong that any mountain should be flattened instantly, like a sandcastle being crushed by an ocean wave. These cosmic mountains reach heights of just a few centimeters, barely taller than your thumb. But given the extreme conditions on a neutron star, their very existence is as shocking as finding an ice cube surviving in the center of the sun. The fact that they stand at all suggests something extraordinary about the properties of matter under extreme conditions. When neutron stars spin, these tiny mountains create ripples in spacetime called gravitational waves. Picture a spinning ice skater with a small bump on their costume. As they spin, this irregularity creates a pattern. Similarly, as neutron stars rotate, their mountains create patterns in the fabric of space that we can detect with sensitive instruments on Earth. The existence of these mountains tells us something profound about the material neutron stars are made of. Their crusts must be incredibly strong, stronger than any material we know of on Earth. Imagine a material so strong it can maintain its shape under pressures that would instantly flatten a diamond into atomic dust. Scientists think these mountains form when the neutron star's crust cools and solidifies, similar to how Earth's tectonic plates can create mountains when they collide. But the physics involved is far more extreme. The pressures and densities in a neutron star's crust are so intense that atomic nuclei are squeezed together, creating exotic forms of matter we can't reproduce in laboratories. Detecting these mountains directly is impossible with current technology. They're not only incredibly small, but neutron stars are typically hundreds or thousands of light years away. Instead, scientists look for the gravitational waves these mountains create as the star spins, like listening for the hum of a slightly unbalanced washing machine from several cities away. Advanced gravitational wave detectors like LIGO can pick up these cosmic vibrations. Each detection helps scientists understand more about how matter behaves under the most extreme conditions in the universe. It's like having a window into a natural laboratory where the laws of physics are pushed to their absolute limits. These discoveries challenge our understanding of nuclear physics. On Earth, we can only study nuclear matter under relatively mild conditions. But neutron star mountains give us clues about how matter behaves when squeezed to densities millions of times greater than anything we can create in our most powerful particle accelerators. The mystery of neutron star mountains connects to bigger questions about the nature of matter itself. How does matter behave when crushed beyond any density we can imagine? What unknown properties allow these tiny mountains to exist? Each new observation brings us closer to understanding these fundamental questions about the universe. Future gravitational wave observatories will be even more sensitive, potentially allowing us to detect smaller mountains and study their properties in greater detail. This could reveal new insights about the structure of neutron stars and the exotic states of matter they contain, helping us understand the building blocks of our universe under the most extreme conditions nature can create. What makes these cosmic mountains so fascinating is not their size, but what their existence tells us about the limits of physics. In a place where gravity should crush everything flat, these tiny mountains stand as evidence that the universe still holds secrets about the fundamental nature of matter and force. For billions of years, the universe has been expanding in all directions following the Big Bang. Scientists long assumed this expansion was uniform everywhere, a principle called isotropy. But recent observations tell a different story. When astronomers look deep into space using X-ray telescopes, they've discovered something extraordinary. The universe appears to be expanding at different rates depending on which direction they look. This discovery emerged from studying hundreds of galaxy clusters scattered across the cosmos. Scientists used NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton spacecraft to observe 313 galaxy clusters, along with additional data bringing the total to 842 clusters. These massive collections of galaxies serve as cosmic beacons, allowing astronomers to measure the universe's expansion in different directions. The technique relies on a fundamental relationship between a galaxy cluster's temperature and its X-ray brightness. Hotter gas in these clusters produces more X-rays in a predictable way. By comparing the actual brightness they observe with what they expect based on the cluster's temperature, scientists can calculate how fast these clusters are moving away from us. What they found challenges one of cosmology's foundational principles. The clusters appear to be moving away from Earth faster in some directions than others, specifically toward a region between the constellations Centaurus and Vela. This movement occurs at nearly 2 million miles per hour, creating a pattern that cannot be explained by our standard models of cosmic expansion. The implications are profound. The universe's expansion rate, which we thought was uniform, shows variations that suggest space itself might have different properties depending on direction. This finding threatens a cornerstone of modern cosmology, the cosmological principle, which states that the universe should look roughly the same no matter which direction we observe it from. Scientists have proposed several explanations for this cosmic asymmetry. One possibility involves large groups of galaxy clusters moving together under their mutual gravitational attraction. While such correlated motions are common on smaller scales, up to about 850 million light-years, This new evidence suggests similar movements might occur on much larger scales, up to 5 billion light-years from Earth. A more radical explanation suggests that dark energy, the mysterious force driving the universe's acceleration, might not be uniform throughout space, like uneven yeast in bread dough causing different rates of rising. Varying strengths of dark energy could cause the universe to expand faster in some regions than others. This would fundamentally change our understanding of both dark energy and the cosmos itself. The research team analyzed their findings using multiple methods and datasets to ensure their results weren't due to observational errors. They combined information from 3 major X-ray observatories and carefully accounted for various factors that could affect their measurements. The pattern of anisotropy remained consistent across different analyses. This isn't the first hint that the universe might not be perfectly uniform. Previous studies using other methods, including observations of exploded stars and infrared galaxy surveys, have produced similar suggestions of cosmic anisotropy. However, this X-ray study provides independent confirmation using a completely different technique. The method relies on the kinematic Sunyaev-Zeldovich effect, where X-rays from hot gas in galaxy clusters scatter photons in the cosmic microwave background radiation, the afterglow of the Big Bang. This scattering creates a distinctive pattern that allows astronomers to measure the cluster's motion with unprecedented precision. If confirmed, these findings would require a significant revision of our cosmological models. Most current theories and calculations assume the universe is isotropic, especially at the vast distances probed in this study. If this assumption proves incorrect, countless astronomical calculations and theories might need adjustment. The discovery particularly challenges our understanding of the early universe. The isotropy of space is thought to have been established during cosmic inflation, a period of rapid expansion immediately after the Big Bang. Finding significant anisotropy now raises questions about this early period and the mechanisms that shape the cosmic structure we observe today. The study of cosmic anisotropy connects to other major mysteries in cosmology. It might relate to the origin of large-scale structures in the universe, the nature of dark energy, and even the possibility of physics beyond our current theories. Each new observation adds another piece to this cosmic puzzle. Scientists continue gathering data to confirm and refine these findings. Future observations with more advanced telescopes might reveal more details about these directional differences in cosmic expansion. The goal is to map these variations more precisely and understand their underlying cause. The observational evidence comes from multiple independent sources. Besides X-ray observations, scientists have detected similar patterns in the cosmic microwave background radiation and in the distribution of galaxies across space. These different lines of evidence, using different techniques and observing different phenomena, all point to the same conclusion. The universe might not be as uniform as we thought. Understanding cosmic anisotropy could provide crucial insights into the fundamental nature of space, time, and the forces that shape our universe. It might help resolve other cosmological puzzles, like the tension between different measurements of the universe's expansion rate, known as the Hubble tension. As telescopes become more powerful and observational techniques more precise, astronomers continue to map these cosmic variations in greater detail. Each new dataset helps constrain possible explanations and moves us closer to understanding why the universe appears different depending on where we look. The mystery of cosmic anisotropy reminds us that even our most basic assumptions about the universe might need revision. What we once thought was a uniform cosmic expansion might actually be a more complex and nuanced phenomenon, reflecting deeper patterns in the structure of space and time that we are only beginning to understand.